But I know there's people in the waiting room. Let's see, what else can I see?
All right, I went ahead. I think I'm live on my channel. I just went ahead and started it just to get it going, make sure everything's going. I forgot to test everything, so just to let you know. All right.
Sounds good. Have you got any folks in your chat?
Oh no, not yet. I just went live, and I probably won't get any for a while. I don't really have many. I haven't really been making too many videos or keeping up with that.
Okay. Yeah. I haven't been doing much either.
Yeah. I did invite someone from my chat that if you remember that DE Banner guy or whatever.
Yeah.
Yeah, so he had some
either
questions.
Here or was here. He was here at 7.
Oh, cool. Oh, cool.
So hopefully he'll pop back, or he's
Yeah,
around.
he said he had some stuff to ask you about.
Okay. 3 minutes.
Yeah, maybe there, even though I did a 5-hour word. Okay, yeah. So Jaren's just grabbing something to eat real quick. He just did a 5-hour stream with someone else.
Oh, yeah. Okay. He's going to need a break. I had a question earlier come in on the chat that we can do first, and we can also do, and then we can do yours.
Yeah, sure thing.
And see if anybody else comes in, like Dr. Banner, FES, maybe has some questions.
Yeah. Oh, yeah, Dr. Banner, your boy.
Dr. Banner.
What was that from? The hold on, don't tell me. One of the Batman or Incredible Hulk, right?
Although that's Bruce Banner. Isn't it Bruce Banner, or is it David Banner? No, it's David Banner.
Bruce Wayne.
Bruce Wayne, David Banner, right?
Yeah, David Wayne. I think is his brother. Weren't they brothers? Don't they, right? Or something?
Hulk. I'm just saying Hulk.
Yeah, we got to do a full Hulk investigation now. We got to get to the bottom of that.
That's the important questions of the night.
Yeah, we're here to solve the great mysteries.
Was the name.
All right.
Was the name of the Marvel character. Okay. All right.
Oh yeah, let me pull up your channel.
Okay, I need to mute this. Interesting. The chat comes in on YouTube much quicker than it does up on StreamYard. It's interesting. Okay. It's time. So I'm going to go live. Here we go. You ready?
Yep.
You're already live, so.
Yep.
Going live. Welcome. We are live. All right. Welcome to I Can Science That, featuring space audits. So we're live, I think, on both channels. Just waiting for my video. There we go. All right. Hey, so we got 12 people, 13 people already. We are expecting a few other guests soon, but we're giving them a bit of a break before they join in. Alan, you want to introduce yourself? You're a frequent on the channel, but you can do an introduction.
Yeah, so I've been looking into flat Earth and stuff for a long time, and I came across Like in Science That's channel, and I found him to be literally the only person online that doesn't act like a giant piece of doesn't put people down when they have an alternative perspective. Rather, he tries to um, make you think about it critically and kind of go through the process and all that and really re-examine it. Now we all have our own biases and stuff, but I appreciate his approach to it, and I find him to be the most genuine person for this kind of stuff. So when you have questions, as a flat earther, like you can't just Google, some crazy, you know, some crazy situation that you can't just like read up on Quora, right? Because everyone's got a different opinion. So like you rather hear it from someone within the what's it called? Like within that credentialed paradigm where like they're quote unquote certified to kind of like speak on and those sort of things. So like you can kind of get a better idea of what's going on, and I really appreciate Matt doing that. And I like to come here and ask stuff, figure out things and how it applies to the way that the worldview that I subscribe to, and kind of compare and contrast and stuff. And I think that let's see, what else did I have on that? That's just why I'm here and why I keep coming back and stuff. And a lot of these conversations get heated, and it leads to people like if you ever see people talk about religion, like how long before they're yelling at each other, right? There used to be an old the old etiquette was never talk religion or politics, because right. But then nowadays everything's like, what's your immediate political affiliation and belief system and stuff, and if it's not mine, then we're going to argue. And I think that's by design. And I think that I think what we're doing, having conversations together, even though we disagree on a lot of things, it shows people that you don't have to freak out about, you can be normal, and people are people regardless of what they believe in or why they believe it. And if you can't put yourself in someone else's shoes or try and see why they see things a certain way, then like the problem's really on you. Like if so anyway, that's my little speech. I'll hand it over to you, Matt.
All right, cool. As I said, we are expecting a couple of at least two other guests, and then maybe we'll open it up to have other people join in if there's somebody else who wants to come. I got some slides to remind me what to say. So yeah, what we're doing tonight is what we're calling Ask Me Anything, just a series of questions that we are collecting from people who I like to call like a science contrarian, somebody who isn't happy with just what the textbook says, somebody who has deeper questions. And so we're not going to debate, and we're not going to argue. We're not going to have a dumpster fire. We are just going to treat these questions as if they are genuine curiosity. And hey, there we have another guest here. Let me add you to the stream, sir. Jaron, can you hear us?
I can, I think.
All right, cool.
Indeed.
Well, welcome to the channel. I was just saying we're not gonna have a debate or an argument. It's not gonna be a dumpster fire. We're just gonna genuine curiosity about some questions, things that don't make sense, or it's not intuitive, or how does this work? Can you just explain it? And so that's what we're gonna do. Okay, format. I'm looking for just quick questions, so I'm going to try to hold it to 2 minutes for a question, one topic at a time, and then I will try to give a 2-minute, TLDR type of answer, and then after that we can go back and forth and follow up, and like until everybody's satisfied that the answer was provided to the extent that you need it. All right. Okay, let's talk real quick where we're coming from here. I will be giving the mainstream science answers, and I've invited you folks to come on because that is not your position, right? Your position is going to start from as opposite as you can get. And we understand we're not going to change each other's mind about that, and that's okay. Instead, we're just going to have a friendly discussion about science. You're going to ask some questions. I'm going to do my best to answer them. We're going to have a back and forth about that. And I will not be trying to convince you that the Earth is round, but I am hoping I can convince you maybe just at least a little bit that these types of questions have answers. And the answers are consistent from my point of view, right? From the mainstream science point of view, there are consistent answers for these things. Okay. Yeah, all right, so that's it. Jaron, did you want to introduce yourself a little bit? Anything?
Yeah, Jaron from Jaronism. You can call it a science contrarian. I guess it's just skeptical. Skeptical used to mean people were skeptical of everything. Now it means you're skeptical of religion and you dogmatically believe everything that science tells you. So it's kind of definitely changed its tune versus what it used to be. My question for you is, do you ever see globe believers concede anything? Have you ever seen them concede anything?
Absolutely, all the time.
Like name one.
For example, when I first got into this, I thought that when you look straight across a refraction gradient, that should not cause the light to bend, because I imagined things as like layers. So like you were looking straight through like a layer of glass, and that should not cause the light to bend. And then somebody pointed out, hey, look, here's a laser. I'm showing that it does bend. And I was like, oh, well, look at that. It does bend.
Which way?
So it bends towards the direction of the greater index of refraction.
And does it bend up or down?
It depends on which way the index of refraction changes.
Well,
typically, we'll get into that later. But this is an example. You just wanted an example.
Well, that's you conceding. And
yeah, I was gonna say you're the only one I've literally ever seen go, oh yeah, good point. Like for example, when I did the satellite thing with you, you're the only one in the entire, heliocentric proponent or enthusiast paradigm that's ever gone, oh yeah, you know what? I could see that could work. You're right. Literally the only one. You should see what happened to that Bryant guy when he came across this information. Like it broke his mind. He literally was like, no, Paul, on the plane, this isn't what it is. And then he reads what it is, and it's exactly what Paul said. And you could just see that his brain just doesn't work now. So like so you're literally the only person, bro. Just a heads up.
Fair. And I want to highlight that that is really kind of the reason I built this channel the way that I did, is because I saw a lot of really heated, just like dumpster fire style debates where nobody concedes anything on either side. Nobody's learning anything. They're just shouting at each other. Right. And I thought that's ridiculous. That's not how we work in the educational world. That's not how science is supposed to work.
It's not how anything works. Really.
Right. It's entertainment. I think it's just entertainment.
Right. And I think that the difference is that the flat earthers that got involved in this are not here for entertainment. Now, I know I have to keep some of my videos funny and I've got to throw some things in there. Otherwise, I'm not going to get very many views. But as far as Globers who made their channel and their main goal is to make fun of flat earthers to no end, it's a little bit different. You're not going to get very far in that other than just to piss people off, gaslight, and get a bunch of teenage boys to follow you and think you're cool. So let me get to my first one. I had two questions I wanted to get to you tonight. Okay. The first one is, can you help me with the Ranty long distance observation? Can you get me can you show me where that location is? Because I'm trying to do it on Google Earth and I cannot even figure out where that location is from. And then the exact height, distances, just so I can play with that observation myself. And then if you bring up your short version, you have a video called, observation short. It's just you doing a little test on the floor.
Okay.
Can you bring that up and show it to me? Because
let's do one thing at a time.
Okay.
So you did tip me off or Alan tipped me off that you wanted to know the Blackpool Tower thing. So I spent
Yeah.
some time this afternoon finding that.
My man, thank you.
Yeah. So I mean, because it takes time, as you know. That's the problem.
Yeah, I was looking for it today. I think that I ended up realizing I was on the complete opposite side. It's kind of weird because you're looking at the picture and you see the Blackpool Tower on the right and the roller coaster on the left. Yeah, here. So I think I had myself looking in the complete wrong direction. Now I realize I think this is on the, I don't know whether that would be, you know, past the shore. So basically in this picture here, the Blackpool Tower is further than the roller coaster, correct?
I'm sorry. So this is the,
from this view here, if you're talking about which one is closer to you, the
roller coaster I think is closer.
Okay, I think that I was trying to look at it from the other side, and it still you can still make it on the left because you're just looking from the other way at an angle. But then it caused the mountains to be like 60 miles away. So go ahead and give me the kilometers. Where are you from?
I'm actually I'm in California, so miles is my native speech as well.
How dare you?
But I did this in kilometers and meters.
Okay, I can use a calculator, I guess. All right, so the observer is 0, and then we've got the tower at 19.63 kilometers. Then we've got Dow Crag is one of the tops of the peaks.
One of the mountains is called Dow Crag. One of them, there's a couple. I just picked 3 mountains from this shot. This one that's right behind. Yeah, you can't see that. You can see this though. This one is Dow Crag. This one is the Old Man one. Skeffel Peak is, I think, this one. We'll see it here in a second, exactly which one's which.
Okay, let's hope that big one isn't the one you said, or else it doesn't look like that's only 0.01 difference in height. But okay, Skeffel Peak is 91.30. Okay, and then I need that's the elevation
above sea level.
So the observer is 7 meters above sea level.
Mm-hmm.
And that's not the sea right there in the picture?
These are people here, right? And they're walking on the shore.
Right.
So the sea is, so the eye level is probably right about there. Right.
Yeah, it's 21 feet, seems like a bit. Okay. So 7 meters. And then Blackpool Tower deck is 120 meters. Wait. Okay. Wait, that's
this thing. That's the observation deck where people
gotcha.
Where people live. People can go. And then if you want to go to the tippy top, that's the 158.
Okay, 158 meters. And then we've got Dow Crag is 778. That's the peak?
Yeah. The peak of...
Okay, 778. I got you. 778 high. And then 803, and then scaffold 970. Okay. Got you. Okay. And now let's look at your example video.
Well, hold on. I just wanted to give you this. Found it on Google Earth, the location where
good.
The guy was...
Can you copy that somehow and put it in a chat or anything, or no?
Yeah.
It'd be easier. For me.
Okay, that's the Google Earth link. And while I'm here, let me shoot you a peak finder from that location as well, which is how I kind of confirmed that is the location.
Where did you put it? Sorry.
In YouTube chat.
YouTube chat? Is that you getting that? It might be a delay.
No, I was looking in the private chat on StreamYard.
Oh, I could put it in the private chat. I'll put it in the public. Everybody can see it.
Yeah. Thank you.
Okay, and I have that open.
Okay, so go ahead and you can wait, I gotta get back to see.
There you go.
Where you're at.
It's right here.
Are you sharing?
Oh, I'm not sharing. As soon as I turned off presentation, looks like the share stopped. Okay. Share the screen on the right-hand side. Go. Okay. So this is the location. It's Southport. And they look across this little bay to Blackpool, which is up here.
Okay. I don't know why mine's not opening, but.
And so, yeah, where do we get the idea that it's at 7 meters?
checking mine, see what it says. Yeah, so it does say 7. Okay, gotcha.
Yeah,
Maybe
it's 6 meters.
Yeah, I see.
Add 1 for the tripod.
Okay.
Right.
Agree.
Yeah, so 6 meters there. So, okay, and so that's that one. And so then what did I do? Let's do. You seeing this?
Sorry, can you get back over there? I just see Google Earth.
Okay. Sorry, my streaming skills are not professional level.
You're not up to my level. I get it.
No. I'm a noob.
My
I'm a
computer
pure
skills
amateur.
are-
I'm a pure amateur, you guys.
What the hell's going on here? Is it open over here?
Okay. And so there's that shot, the famous shot. And here I have overlaid Peak Finder for you from that location to confirm that's the correct location and give it these labels of all these lovely
I want to see if my
mountains for you.
Because I've got a picture of the 3 mountains here. So then the one right behind it is Dow Crag. Yep.
Yeah.
Then the one to the right of that would be Swirl How.
I'm calling it Old Man of Coniston. Although it's interesting to discuss the difference between Old Man and Swirl How, where they're at the same height.
Okay.
But Swirl How is much shorter.
And then the one on the left would be Bowfell.
Bowfell.
I don't know. I'm just looking at.
Oh, Bowfell. That's right here.
Okay.
That one.
Yeah, it looks the same as what I have. Okay, good. And then there's one called Hard Knot. Okay, you have that one, 549. Hard
Knot looks to be this.
And that's 549 meters. That the height of that little thing.
I guess.
Okay, I have the same thing, 539, and it is showing that one down there low.
I never investigated that one personally.
Okay,
but
and then I just want to go from there to your video that you did.
Okay, the video. Well, it's going to take me a second to get that up.
I can find it very fun. I was looking at it the other day.
Yeah, you want to bring it up?
Sure, I'll bring it up. I'll give you a link. And let me find it for you.
I think I'm talking about share if you want.
Oh yeah, I can do that too. Let me show you. Let me go there and find it. We got videos, and it was called. It's about a year ago. No, I don't see it. Where is it? Hold on, I saw it today. Oh, I see it now.
Was the ones where I just had paper cutouts? That one?
Yeah, I just don't see it. I'm seeing clips from Alan's live stream. Live stream. And that would have been about a year.
Oh,
wait, I think I found it. It's way.
You found it?
Yeah, it's still a year back.
I have the original here somewhere, but
okay. So I'm going to bring up this one. This is the short version, and I'm going to share my screen.
All right, take it away.
Screen share, present video. No, share screen.
You have permission.
Screen. Okay, and you see it here. Nope, there. Right.
There you go.
Okay, so my question here is, I got how you did the experiment and everything, but what I didn't get is here when you are zooming in to show that the mountains are certainly appear to be higher. You say that we can take a okay, so what's going on here?
I'm moving the camera up and down.
So by doing that, you now made the tower above the mountains.
Right, right.
So then isn't that the answer?
Well, but then the camera would have to be below the ground.
You put the camera below the ground here?
The ground level in this example is the bottom of the 2 pieces of paper. So if the 2 bottoms are lined up perfectly, then the camera is exactly at the same level as the bottom, right? At sea level. Sea level is the bottom of the papers.
Oh, I didn't know. The bottom of the papers is sea level. This?
Right, right. The bottom of the papers is sea level.
So you're lining them up and then?
Yeah, that way when I move the camera up and down, I can let the viewer decide when they think it's lined up, as opposed to me deciding I think it's lined up here. Because, it's fuzzy. There's some qualitative decision to be made about when they look lined up, right?
You're saying your camera lens is exactly this height above the ground.
I'm saying in this video that you're watching, I'm moving the camera up and down.
Well, we shouldn't be doing that, right? The camera needs to be level with the bottoms of the tower and the mountain.
Correct. That's right. And so how do we achieve exactly level with the bottoms?
I don't know. Why wouldn't you
did it. The way I did it was by moving it to where it's too high and down through too low, with the understanding that there must be a moment between there where it's exactly right. And I let the viewer choose when they think that moment is.
Okay, and then you're saying this, so this piece of paper here is a certain height, and then the red paper is 5 times that high. 5 times that much.
I don't remember if it was exactly 5 times, but this was specifically meant to duplicate Rachel's example, which I don't think her numbers were exactly the same as what it should have been for Dow Crag and the Blackpool Tower. She got a very interesting result, and so I was investigating whether her result could be replicated.
Okay, so according to what I have here, 978 divided by 158 is 6.18. So your back piece of paper is 6.18 times the size of the small paper?
I don't think it is. I think I was using Rachel's numbers for the papers, and so understanding I'm not trying to investigate Blackpool Tower with this video.
Oh, I didn't know that.
This is a response to Rachel's video on the subject.
Okay,
if you
so
look
let me
in the
ask you that.
description, I'm sure hers is linked.
Do you think it is the case that we should never see that mountain behind the tower?
You should never.
You should never see the mountain at a lower position than the tower if the Earth is flat.
I would say if you did see that on a flat Earth, that means you had an extreme refraction situation of some kind. Or, I mean, maybe we could even widen the question and say, light did not travel in a straight line.
So whenever we have evidence that leads to a flat Earth, we just assume that it means that something happened on the globe that caused us to see flat.
No, what I just said was,
well, what I'm saying is there's no amount of evidence that you're going to take and say, oh, that's interesting, that leads towards a flat Earth. You're going to take any evidence that goes opposite of what we should see on the globe and say the reason we see that is because of some sort of abnormality in the refraction causing us to see something we normally wouldn't on a globe.
Okay, I'm just not even going to answer that. We're doing a series of questions one at a time, and it's supposed to be just quick questions. You're not supposed to be like argumentative, right? That question seems very argumentative. Okay.
Yep. And then so
we'll circle back to it. Let's circle back to it sort of in a conclusion or something. But let's just do the questions.
Yes. Okay. So I got your questions. I now got the distances down, at least per what you think the distances are. Hey, did you get that from Ranty or no? Well, Ranty didn't take this photo, correct?
He did not.
Okay. Gotcha. And does it ever matter if we use various kinds of lenses, telephoto lenses? Would there be types of lenses that would cause something to happen that we wouldn't normally see in your mind?
Lenses can create distortion, like barrel distortion. You mean like that?
No, I'm more talking about there's certain images that I've seen before that use a telephoto lens, and they actually make things appear to be something that they're completely not, right? So maybe you're looking down a long street and you can take a photo that has a very in focus mailbox, and right behind it is a car, and they're right next to each other. But then when you actually put a regular lens on it, you realize, oh my goodness, those are 3 blocks apart. It's just the telephoto lens brought everything together.
Sure. That sounds like you're describing compression. What we actually, the real world description of what is compression. Which is when you zoom in, your field of view becomes very compressed, very small. And so things that are far away don't seem as separated as they really are anymore. It's interesting. in my perspective video, I have a little clip from somebody else's where they show this. Like there's a trick in photography called a focal length pull. You know what I'm talking about?
Mm-hmm.
Yeah, where it creates really weird, like spooky kind of feel when they zoom in on you while also pulling back, so that the actor stays still or stays the same size while the background seems to
like
expand
zooms
on you.
Or yeah, and it expands. I was going to see if I could find the image I'm talking about, because I actually remember where I first ran into it was during the San Bernardino event, but I don't see it.
I'm going to pop that off. I don't want to have any like scenes of violence on the discussion, if you don't mind.
No, you can take it off. There's a picture where you're looking down that street where the same thing happens. And at first I was like, what? That seems totally fake, because the mailbox looked taller than the car. And I was having issues with that. And then realized when you actually look at that location, that mailbox is 3 blocks closer than the car. And that's the telephoto lens brought it so close, both the car and the mailbox, that the mailbox then appeared taller than the car at a faraway distance. And I've always thought that was weird and thought, well, the car is taller than the mailbox. Why? And how could the mailbox be taller than it? But of course, it's a perspective thing and a telephoto lens thing.
So yeah, I would just say the quick answer there is that the lens will not curve the light before it gets to the lens, right? The light coming from the world is going to pass in a approximately straight line toward until it gets to the lens, and then the lens is going to bend it and distort it, right?
Right. So if we're looking through let's say it's a standard atmosphere, or it's a homogeneous atmosphere, we're just looking straight ahead, and something is on the far end of that observation. Let's say it's a building. As that light is traveling to us, it's going to bend down, correct?
Okay, standard atmosphere isn't quite homogeneous now, right?
No, I'm saying, let's say it's homogeneous. Homogeneous, I mean, it's the same throughout.
Then it will not bend.
So even though the light keeps hitting more and more and more and more atmosphere, it just stays straight.
Well, if it's homogeneous, I'm interpreting that to mean the same pressure, same density,
yes,
same constitution, then there should be no refraction. The light should go perfectly straight.
Even as it's being retarded more and more and more and more because it's going straight ahead, it doesn't bend down.
The light doesn't get retarded more and more. The speed of light is determined by the medium it's traveling through.
Right.
So it would only slow down like more if it went into a denser medium, if it went into a medium that had a higher index of refraction, like going into glass or going into water.
Okay, gotcha. And if it's just going through regular atmosphere the whole way, the line should stay straight.
Well, homogeneous, like an idealized atmosphere that is completely uniform, and should go perfectly straight. But our atmosphere
probably not realistic, right?
Is not perfectly uniform.
Correct. Okay. And then my last question is concerning the gravity holding the atmosphere to the Earth. I think you knew I was going to come and ask that, so you probably have something planned.
Not really. I didn't know what exactly you were going to ask, but I've talked to Alan about that one before. So
okay, yeah, and that's basically it, right? So that I'm always told that, of course, you can have this atmosphere next to the vacuum of space because the gravity is holding it. But again, we can just do a thought experiment and take a bedroom size vacuum chamber, and we can have a shoebox size of air, and that can be sitting on the floor, and we can evacuate the room, and then we can, electronically open the lid of the box, and every time that gas in the box will fill the vacuum chamber, never will it be held to Earth via gravity. So therefore, if it cannot hold the small amount of air inside the shoebox to the Earth, how is it holding the massive amount of air of the entire atmosphere?
Okay. I got a couple of links for you here and a little chart, little graph. This is just, Wikipedia and Engineering Toolbox. You can look at those and see what gravity does to air pressure. And there's the chart, right? Here's your pressure over here. You can see my little thingy. Yeah, here's your pressure, and then here's the altitude. So if you make a shoebox right? I'll just make a shoebox here. Let's make it not filled. Okay, let's say it's our shoebox, and it starts at an altitude of 0, and it's going to go up to an altitude of 1,000 feet. It's a ginormous shoebox.
Okay.
That is the pressure difference you're going to see in the box. It's going to be 100 kPa at the bottom of the box and 90 kPa at the top of the box.
Okay.
Right? That's the box doesn't go. The presence of the box is not what's causing the gradient. It is gravity. So
okay. But if we open the top of that box and it's open to the vacuum of space, all the air in the box would evacuate.
I don't understand if you open the top of the box, it would not be exposed to space unless you put the box in space.
Okay,
is
so
the
let's
box in
say,
space?
Well, we just said that my example was the shoebox was in a room that was evacuated, so therefore it is in the vacuum. We took the top off the box, and the air escaped into the vacuum of the room.
Sure.
So why didn't gravity hold the air in the box to the ground?
Because that's the curve. That's the curve that it can follow. And if you look at these, you'll see that.
Hold on, I'm so confused how this has anything to do with what I'm talking about. Again,
it's a very gradual. This curve is very gradual.
Okay, so we have a room as big as the room you're in right now. We can evacuate if we want to. Okay, so then we have a shoebox of air sitting on the ground. It's got an electronic top that we can open and close with a remote control. Okay, now we evacuate the room. It's complete vacuum, or as close as we can get it. If we press the button and the top opens from the box, what's going to happen to the air that's in the box?
Most of the air is going to just go right on out.
Okay, so then if gravity can't hold that to the Earth, why is it holding the entire atmosphere to the Earth?
Okay, because what you're describing is not how gravity works. It's not analogous. It's
how so?
You have to, when you want to use what the gravity equation says will happen, you have to actually use the actual gravity equation. Is what I'm saying. Alan, did you want to jump in there?
Yeah. So they say that Earth already lost its atmosphere before, and then it grew another one from volcanoes, right? Like that's like the mainstream narrative of how they got it. So you're saying well, hold on. If it doesn't keep it in the shoebox, how could it rebuild itself from nothing? If the surface level pressure of Earth was the same as the vacuum of space, because they say it lost its thing. Because back when the conversation that we had, you said something that really stuck with me, and it was that the atmosphere is pushing against itself in your model, right? So that like it's the barrier is itself because it's already engulfed around the Earth, right? So if it, yeah, go ahead.
There's a comment that your mic is a little loud. I was right about that.
It's a little hot.
Oh, sorry about that. Let me turn it down. Apologize.
Okay. I don't think whether the atmosphere was acquired or when it was lost is relevant to the shoebox. Let's stick with the shoebox. With the shoebox, Jaron, you're describing a gradient to go from atmospheric pressure of 14.7 to 0 over the size of what, 6 inches? Your shoebox. How tall is your shoebox?
So we can redo it if you want and call it. Here, I'll show you a different version here. So if we have now, well, that's kind of hard to see, but let me share my screen over here.
Okay, I'm going to stop mine.
I'm not showing any graphic
okay.
Murder scenes. Okay, and let me go share. Can you share it again, or do I have to press it again?
Yeah, it's on. It's on.
Okay, good. So now if we've got this kind of,
now. There you go.
So let's say instead of a small shoebox, we actually can take the shoebox all the way up to space. If that's
just an imaginary ginormous shoebox that's like
correct. So it's
100
like
miles tall.
Yes, it's like this. It's this big box, and in this box is air. And then at the top, we open the lid to the vacuum of space. You're saying that the air in this column would be held to the Earth by gravity. It
Well,
would
I'm
not
saying
escape out to space.
before you even opened the lid,
Okay.
you would find that the bottom of the box is at atmospheric pressure, and the top of the box is a vacuum.
Okay, so you're saying that the vacuum, the pressure of the atmosphere would be 1 here. Oops, I thought I was drawing in the color.
1 atmosphere, sure.
Right, 1 atmosphere here. And then you're saying that because there would be some sort of gradient, so we'd have a lot of air here, and it would get lighter and lighter and lighter and lighter until we get to the vacuum here.
Yeah.
And
yeah, it's not caused by the container. It's just caused by, the gravity causes that gradient. So it's going to happen, container or no container.
Sorry, is my mic better now? Does it sound good?
A little better. It's a little loud, but it's okay.
I can move it away. How's it now?
That's better.
Okay.
I think you sound okay.
So in the pre-established gradient of the shoebox before it's exposed to the vacuum of space, right? And then after you expose it to the vacuum of space, that gradient's going to pretty much go away, right?
Gradient's going to stay exactly like it is.
Oh, right. Yeah, I forgot you would. Yeah, that's what you do believe.
The gradient's not caused by the container. The gradient is caused by gravity. So the size of your container has nothing to do with the gradient. And in fact, you can demonstrate this. Take a long pipe and put a pressure transducer on both ends, right? And lay it horizontal. And you should measure that the pressure is approximately the same at both ends of the pipe. Now rotate the pipe upright, and you'll see the pressure increases on the bottom one and drops at the top. You'll get a pressure gradient just by turning a pipe upright, and it'll go away just by laying it down.
And so you're saying with this one here, but if we then do the test like this, you're saying that immediately the air, when we opened it, would leave.
Well, you'll get the same gradient, but notice if you're 14.7 at the bottom, then 6 inches up, you're pretty much still 14.7. It takes 100 miles.
Well, then, but hold on, then
for that gradient to go through its. What's that?
If you've got 14.7 here, and we take the top off, you're saying the 14.7 would have to stay there.
No.
Okay.
No, that's not what I said.
What'd you say?
I said that the gradient, right?
This gradient here.
1 atmosphere is 1 atmosphere at the bottom.
Yes.
And it's 0 up at 100 miles.
Yes.
And it drops in a smooth curve over that distance.
Okay.
That distance will not change regardless of where you put the lid of the box.
Okay. So now here, then
so it takes all 100 miles to get that, for that gradient to get to near 0, right? So if you make a short box, you don't get the whole gradient. You only get the very bottom part of the gradient.
But the bottom part is the 1.
Yeah. So you're not going to see any effect here. You need a long pipe to see that slight gradient taking place.
If the air is in here, causing it to have 1 atmospheric pressure, and the air is in here, causing it to have 1 atmospheric pressure, when we open the lid of this box, you said it would go into space.
Right.
So then it's not remaining at 1. It would be empty.
Okay.
Maybe I'm not understanding what you're saying.
I guess you're not. The tall pipe on the left.
This one.
Yeah. When it was sealed.
Sealed, okay.
Naturally created a gradient from 1 atmosphere at the bottom, 0 at the top. Approximately 0 at the top.
Naturally because of what?
The force of gravity.
Okay.
Okay, and you have no problem with that?
Well, I mean, obviously I do, but I can understand what you're saying, that if there is a downward pulling force here, that it would pull basically as much as it could, and then it's not going to be able to pull some, and then it's going to level out, I guess, or even out.
Right, right.
This is before we pull the top off.
Okay. In fact, let's try to take it out of a controversial thought process into something I think is not controversial at all.
Okay.
Instead of filling it with air, let's fill it with water. Let's take a pipe full of water.
Okay.
Okay. If you take a pipe.
I'll do 2 pipes here of water.
Okay,
so we got 1 pipe here.
A tall pipe and a short pipe.
How short you want it?
I think somebody who knows the number can maybe correct me. I'm thinking it's like I don't know, it's like 50 feet, something like that.
Okay, maybe we'll do it like that.
Okay, and what we'll do is we'll say the blue at the bottom is a pool of water. That's
Down
open.
Here?
It's open to the air. Yeah.
Yeah, it's like an ocean or something.
It's open to the air. Okay. If you try to suck the water out of the top of the pipe,
okay,
you cannot at a certain level. There's only so high that water can go. That makes sense?
If we tried to suck it out here with like our mouth?
Maybe I'm taking it too complicated.
Yeah, you lost me with that one. I had a better time understanding what you were saying before, that it just already naturally sorts itself, and then when you were to expose it to the vacuum of space, it wouldn't change anything.
Well, okay.
Right.
Well, all right. We'll stick with the water. I won't do the open at the bottom. We'll close it at the bottom. So it's just a container, tall container of water.
Okay.
Okay. And if you open the top of the container, the water doesn't spill out. It just sits there.
Okay. Or it probably would boil, but we'll not say that. Okay.
Okay. But instead, what I want you to do is take that top of the well, no, this is not, it's not a million miles long. This one's just like, make it 50 feet long, right?
Okay.
Reasonable amount. Something you could actually do. But instead, now compare the other one. It's only 10 feet tall, right? So what we'll do is we'll take the 50-foot tall box.
Okay.
That can hold water. It holds water just fine, right?
Yep.
And now I want you to cut the top 40 off. We're just going to take a saw and just cut right across.
Here.
Yeah, that's fine. Okay, that's fine. Yeah.
Okay.
Saw, you cut right there. How come it can't hold the water?
The pipe?
The water in the top of the pipe falls down now, right?
It's got nothing to contain it.
Yeah. So how come the pipe on the left could hold that water, but the pipe on the right can't hold that water?
Pipe on the left can hold what water?
Okay, I'm not saying that well. Before you cut it,
right.
The pipe could hold the water. The taller pipe holds more water.
Yes.
Than a shorter pipe.
Yes.
Why is that?
Because it's taller.
Okay, so let's just do it with air then. On the left, the squiggly lines, we saw that the taller, we called it a shoebox, all the way back to the air one.
Okay.
The taller one can hold air all the way up to the top, but the shorter one can only hold air for a little bit. And that's...
Okay, so I guess where I'm confused is if gravity is pulling down enough that it's able to hold this air and not worry about any of it escaping to the vacuum, I don't understand how it can't hold this air and not worry about it escaping to the vacuum.
Because all those other red lines that you squiggled,
right?
All that air is holding the air down. That's the weight, that the air has weight, just like the water. The water in the pipe.
Yeah, you're describing our version.
The other water
that's
down.
what I believe. I mean, my belief is that because the air has weight.
That's correct.
Right, but there's
no
gravity
wrong with
involved
that.
in that. Well, there's no gravity involved there. I don't need gravity. Why do I need gravity
gravity is the word given to weight. That's what gravity means.
Okay. Well, then we're on the same page. Yeah. I also agree that gravity is not a pulling force. Gravity is weight. And weight,
well, whether that's a push or a pull, I mean, neither here nor there.
It doesn't have to be a push or pull. I have mass, I have density, and so I weigh something, but it has nothing to do with anything pulling me to the ground. The weight is simply weighing me down. I weigh more.
Okay, let's don't argue. Let's just do questions.
Okay.
So I hopefully you find it refreshing that I agree that weight is gravity. Gravity is weight. Weight is gravity. That's what it means.
Gravitas, yes.
Yeah. So air has weight. Something that we disagree about what causes it, but something pulls air down. So just like with the water pipe, if you chop off the top of your air pipe, all the air in the column above spills out, just like the water does.
Okay.
So yeah, that's why gravity, the weight of that air can hold that air down. But if you chop off the top of the pipe, it can't anymore. There's nothing to hold it down.
So you're saying if I cut this here, then immediately all this would leave and all this would leave.
Well, whatever, it would be exposed to whatever's outside the container, and it would, the top surface, the open surface, would need to equalize with the pressure that it's exposed to.
But just the top layer. For instance,
whatever's exposed needs to equalize.
So you're saying this air here doesn't need to go to the vacuum because it's being held loosely by gravity.
Well, it's not exposed to that, right? It's not directly exposed. It's exposed to the air above it, which is exposed to the air above it, which is exposed to the air above it, right?
But this has pressure and this has none. So it would go towards the no pressure.
Well, it will balance.
No, I get you. You're saying that gravity is
what's the weight pulls down, and that's countered by the pressure, right? So if there's pressure pushing it up that's greater than the weight pulling it down, it goes up. If the weight is greater than the pressure, it goes down.
I'm more confused than when I came into this. All right. Well,
same, dude.
Well, I mean, I
thought I understood what you were saying before.
It's very counterintuitive. What you're saying is not intuitive. It's not, it doesn't seem correct. Now I get this. The reason this is confusing probably is because where does the air end and where does the vacuum start here? If this entire black area is a vacuum, would you say the same thing takes place?
Yes. Yeah. Okay. Let me try to make it really, really crystal clear.
Hold on a second, real quick. I just want to make sure. So if we went in a vacuum chamber and we had a open pipe such as this, and we went as tall as the vacuum chamber was and put air in it and then remove the top, you're saying that nothing would leave this.
That isn't what I said. No.
Well, I just asked you.
Let me make it super clear, guys. Let me make it super clear. The air that is exposed, I mean, the two-dimensional surface that is exposed between the contained volume and the exterior volume, that must equalize on both sides of it. The pressure will be equal.
Both sides of the pipe.
So, where is it exposed?
Just here.
Just there. That's right. So at that point, the pressure must equalize.
Meaning that
and
the
then
air
you'll get a gradient on down from there.
It goes there. Okay, so that's what I said. So in a vacuum chamber, if we had a big tube like this full of air, and then we remove the top, that only the top little bits of air would escape into the vacuum and the rest of the air would remain inside there.
The rest of the air would be exposed to the air above it, and it would reduce pressure until the entire container's pressure would reduce until the top surface is in balance.
And the little bits that are here, they don't ever need to move up?
Is that what I said?
I'm asking you. That was a question.
I don't believe that's what I said. I think the top, when you open the lid, the top surface of the air is at a higher pressure than its environment.
Correct. Here, there's pressure here, and there's none here.
Right.
We open it, and so
those little yellow things, some of them fly out.
Okay.
So now, right below that,
right here,
there's now that's not an equilibrium because the pressure above it has dropped. So the pressure below also goes up.
So it goes up, but then since it went up here, it would need to connect. Then the pieces that went up here would need to go out into space.
Not all the way necessarily. They have to go up until it reaches equilibrium.
Okay, and then when it equals equilibrium, then the stuff that's here would need to move up. It would go up here, causing this to push up and causing more to leave.
Yes, but not necessarily all the way. What you seem to be suggesting is that the air at all the air must be in equilibrium from bottom to top.
Correct. That's how gas works.
No.
So if we had a tube like this,
that's not how gas works.
Hold on. If we had a little container like this, and in it we had this, and on this side it was vacuum, and on this side we had air. Okay, and then we have a little door here that pops open like this, and this is on Earth. Okay, so here's the Earth. and we open this little chamber here.
Mm-hmm.
Okay, so a little chamber opens. You're saying that just a little bit of this air would go into the vacuum, and this would remain a gradient. Which is not true.
It is true.
No, you can't have.
It is true. How do you think a vacuum pump works?
All the air would go like this.
No, seriously. How do you think a vacuum pump works?
I think that the entire amount of this would have to have the disbursement of all gas in it.
If that were the case, then you could not have a vacuum pump because the vacuum pump creates a region where there's a low pressure on one side and a high pressure on another side. Doesn't it? That's what it does.
But it's constantly sucking. You can't turn it off and then it still hold.
Right. Exactly. It's constantly sucking. What else do we know of that constantly sucks?
This. Gravity
sucks.
So does a vacuum.
Gravity sucks, right?
I don't believe that, but okay.
Well, okay. Wait. It's constantly pushing down.
So let me just make sure. You do have somebody who has a vacuum chamber who has access to a large one that they do with their business. And we've been looking for an experiment. So you're saying if we get a tall tube in a vacuum chamber, let's say the vacuum chamber is 10 feet high, and we get a tall tube that we're able to fill with air, we seal the top, we evacuate the chamber, we open the top, and he has pressure readings where he can put a little dial on the bottom, on the middle, and on the top of that tube. And you're saying that then once we open the top to the vacuum in the room, that there will be air that will remain in this tube in some sort of a gradient fashion to the top, even though there's a vacuum all around it.
You could set something like that up.
Okay.
You don't have to go to that extent, though. You can do it in your backyard.
How would you do that?
Blue Marble Science did, right? You just put air in the tube, and you measure the pressure at the bottom.
Yeah, but it's not exposed to any vacuum.
Vacuum just means lower than ambient pressure.
Correct. But there is the extreme vacuum of space that would never be fulfilled. It would never be happy. It would never be content. It always is going to be open for any adjacent pressure.
Okay.
No?
Let's back up. The word vacuum just means lower than ambient pressure. Can we agree to that?
Lower than ambient pressure.
Right. So if the ambient pressure is 14.7 psi, and you expose that to 14.0, the 14.0 is a mild vacuum.
Okay, very mild. Okay.
Okay, so if we can establish this with a mild vacuum, why isn't that enough? We can do that I can do this in my own house with a cell phone.
Because a vacuum to me is just... it is what would cause everything in here to leave.
But we just established that isn't what happens.
When did we
know that is not what happens in nature. You can say that it does, but we know that it does not.
How do we know that?
Because the pressure at the top of a mountain is lower than the pressure at the bottom of the mountain.
Yes, correct. But we don't. You're missing the point. We want to prove, or I want to show, that gravity is not holding this air to the ground. So you're talking about doing it without even including gravity or including the vacuum, which are
you don't need to discuss any of that. You just seem to be, frankly, overcomplicating the matter. We know that, and we agree that the pressure is naturally here on Earth lower up high than it is down below.
Okay.
Right? No contention.
No, because in my model, it would be because, yes, down on Earth, you have more air on top of you.
Yeah. It doesn't matter why.
Okay.
It's true. So if I just take a slice of that world and I trap it in a box, is it not still true that the air is at lower pressure at the top than it was at the bottom? Did the box change it somehow?
Well, if there's a vacuum all around it instead of this air, then yes.
There is a vacuum all around it. There isn't. We're in the world.
Okay. There is a vacuum surrounding this ball Earth that you think we're on. The most amount of vacuum there is.
I don't think we're ready to go there yet. Let's talk about your tube.
Let's
take a tube on the Earth.
Okay.
The bottom of the tube's on the ground. The top of the tube's in the air.
Okay.
The top of the tube will be at a lower pressure than the bottom. And we agreed to this, right?
Correct.
It doesn't matter if the tube is open, doesn't matter if the tube is closed. This is a fact.
Yes.
Okay. So how low does it go? If you make a taller tube, does it get lower pressure at the top?
So where is the vacuum start?
We haven't talked about a vacuum yet.
Okay. So we're talking about a sealed tube?
Does it matter?
Well, yes, because I believe if it's open and any part of it is near the vacuum, it's going to escape through that vacuum.
You keep saying near the vacuum. Let's not talk about the vacuum. That seems to be a point of contention. So,
but the vacuum is the most important thing.
Seal the tube.
Okay.
You're going to get a pressure gradient.
Okay.
And this is not under
convention. Do you recognize that we would have a pressure gradient if there was no gravity and it was, as flat earthers describe the atmosphere, as being simply relative density disequilibrium plus maybe a downward vector due to electrostatics or something like that, meaning that then it would organize itself also with air being stacked on top of each other and getting lighter and lighter and lighter as it went towards the top?
I would say what you just did was describe gravity and refuse to call it such.
Okay, so because the difference is that my version doesn't make things into spheres.
Things, right? Does. Well, no, okay, that's good. That's good. We're kind of getting off topic here, but what you're describing is it goes down.
Correct.
In parallel lines down.
I would just think that if we filled this up on a flat Earth with air, that I would expect to see a gradient once it's settled, right? So it's going to settle and it's going to have, because there's more and more and more air sitting on top of it and kind of weighing it down and sitting it down. And okay, there.
Great.
So then same thing would be true in the small box, meaning that the air would also be packed down to the bottom. And would there be a gradient? It would be very slight, but okay, I can give you that. There's a gradient there as well.
There's a slight gradient, but it does not reach as low a pressure in the small box as the big box does, right?
Okay. Right. Now, if this entire black is vacuum, okay?
Okay.
And we remove the top of the box. So now, electronically this opens and electronically this opens. In my mind, all of this air would leave because it needs to equalize. And as some of it starts to go, just like you said before, let me give a little example, that the very first thing that would happen is these tiny little particles here, because they need to equalize, would leave into the vacuum of space, which would cause these pieces here to move into that place and move these pieces into that place and move these pieces. And then since there's new pieces here that need to equalize, they'd leave. And then this would go up and this would go up and this would go up and this would go until all of it was gone, because there's nothing.
That was exactly right until you said until all of it is gone. Other than that, you were correct.
So why wouldn't it all be gone? Just logically speaking, think about what you're saying again one more time, and then I got to be done. I've done too much streaming today. Again, if you're saying that the top always needs to equalize with the outside, at first you're going to have just a couple particles. They're going to leave, which creates now basically a vacuum here. And now there's pieces here that would need to
remember the gradient.
Okay, but
you have to include the gradient. You can't make it go away just because
but everything needs to fill in. So
you have to have a gradient, though. How can you have a gradient if it's all zero?
I'm not saying there would be a gradient. Why would there be a gradient if the vacuum is near this?
Why wouldn't there be?
Well, because I don't have a worldview that says the Earth needs to be a sphere, so I don't need it.
It's just like the water. It's not about worldview. Same thing happens on flat Earth, by the way. This is an interesting thing. Maybe we could focus on that. If relative equilibrium, disequilibrium thing,
okay,
all gravity, all weight points straight down in parallel lines.
Okay.
What you get is an atmospheric gradient, densest at the bottom, and a vacuum at the top. That's what happens on flat Earth.
Okay, so what we're saying is you could then
But you need walls on your flat Earth to keep the air from spilling out the sides.
You would need what?
You would need some kind of walls around the, I'm not sure which flat Earth you think of, like a disc? Or an infinite plane, maybe?
Infinite plane. Yeah, I mean, I would think that there is containment. So yes.
Okay. So you would need, on a flat Earth, you need a container to hold the sides, just like a glass, just like your glass has to have sides to hold your fluid in.
Correct, but it could
does
also be
not
done
need
with,
a top.
temperature
Notice
and stuff,
it
right?
does not need a top to hold that fluid in. It needs sides.
Yes, according to what you're saying, yes.
Notice the gradient. Because it's a liquid, it's a very sharp gradient, very distinct gradient is created. A gas creates a very smooth gradient over that period of space.
Okay, so I kind of drew a little gradient here, right?
Okay.
Okay, so what I'm saying is, as this left to equalize here, which does that essentially drop the vacuum? Meaning, here's vacuum. We can draw it in white so we can see. Okay, so there's we know this is vacuum right above it. Now, as these little particles equalize there, then wouldn't we also say now that then this is vacuum?
Okay, that can be vacuum.
Okay, so now the particles that are here need to equalize with that. They
no,
go
those
up
are
there.
There's a gradient. Those are vacuum plus 1.
What are here?
Yeah, if you're at 0 at the tip top.
Okay, 0 here.
Then it's 0 plus 1, 1 notch down.
Okay, but they need to equalize.
No, they don't.
Oh boy,
they didn't. Look, they didn't equalize before you opened the lid. Why do they suddenly have to
because
equalize
there was
now?
no vacuum before the lid. There was no vacuum before the lid.
The vacuum is not magic. Vacuum is not magic.
Doesn't need to be magic. Here's what I think. Before the lid is opened and you'll say you're closed here, then this is 0.1, right? And this is 0.4, and this is whatever.
Okay.
It goes down.
Sure.
As soon as we open it, this 0.1 becomes V, becomes a vacuum.
What is your vacuum? If you were already down to 0.1, your vacuum is what? 0.5? 0.05?
0.
Well, you can't go to actual 0, right?
As close as possible.
As close as possible. Let's just call it 0. Okay. So now it's 0, and then the one below that was 0.3. It had to drop by 0.1.
Okay.
So
but now it has to equalize with the vacuum.
Dude, it didn't have to. When it was
vacuum?
Hold on. You had 0.1 and 0.4 living next to each other, and you were happy with that.
Well, it was an example, but it would be a gradient, so it wouldn't go 0.1 to 0.4, right?
Right. Right. But you're happy with that. You got no problem.
I've got
but
no
you're telling me that 0.3 can't live next to 0?
Correct.
0.4 can live next to 0.1, and we're okay.
Right.
But 0.3 definitely cannot live next to 0.
No, because when I think of a vacuum, I think of never-ending open pressure, never-ending no pressure. So always, if it has any chance of having an escape route for gas will always take that route.
But that's not correct.
Okay. Yeah, and I understand.
It's not a never-ending no pressure. That's not it. And even if it was
never-ending no pressure.
No, there's no such thing as 0 pressure.
So if I went out into space and I just threw a bucket of gas out there, it would not just disperse in every direction.
Are you getting argumentative again? It feels like this train of argument.
I think no. I
just wanted to answer from a science perspective.
I just did 5 hours of kind of a debate I didn't expect. So
okay,
I'm a little
sorry about that.
But my whole thing is, let me just say this and I'll go. If this,
I want you to say, but
well, I know, but I got to go. But if this becomes a vacuum, and this, and then it has to equalize, well, then this, the way I would describe it is that the vacuum would start eating into this. It would start making this all.
A little. It will a little, right? But it won't continue down.
Why not?
As you're going down,
every
you're
bit
dismissing.
But
as you're going down.
Fill in. Doesn't it just keep filling in upwards?
No. There was a gradient before.
Right? Because there was no.
There will be a gradient after as well.
But you're saying that, but it doesn't. Why we've opened the top? It doesn't have any containment anymore. There's no reason.
Why do you think the container had anything to do with the gradient? We've covered that before. The gradient does not cause the. I'm sorry. The container does not cause the gradient. The gradient was caused by the weight of the air. That was what you said. And now that you've opened the lid, you're imagining that it's going to get sucked out by that vacuum. And some of it will go out, but those that didn't get out still have weight, and they still push. They still push down. That is, in fact, how a vacuum pump works. A vacuum pump does work. It applies a force onto the air to force air to one side, by virtue of doing that, pulling it away from the other side. That is what a vacuum pump does. We apply force to push the air away.
Okay, so is a vacuum pump stronger than the vacuum of space? Or weaker?
That's not relevant.
Okay.
It's not a relevant question.
It is relevant because if a vacuum chamber gets sucked out via some sort of electronic vacuum, it's taking the air out.
I mean, it's just an argument. If you agree that a vacuum pump can have a low pressure on one side and a high pressure on another side because there's a force creating that gradient, there should be no further argument.
Okay, so in all vacuum chambers that when we evacuate them, they all have a gradient left inside them.
Yeah. As long as there's a force field in there, there will be a gradient in there.
Okay, that's good to know because these guys have the equipment to test this stuff. So I kind of have an idea for a test. That's what I wanted.
Okay.
All right. Well, thank you, sir. I appreciate it.
Hey, thanks for coming on. Yeah, we'll try and hit a few other questions before we close it.
All right, and I'll check back and check them out.
Hopefully we'll see you again sometime.
All right, thanks.
All right.
Later.
Peace.
Cool. All right. Alan, did we want to do your question next?
Yeah, please. And before we begin, though, is my mic better?
Your mic is great, Sweet. I think.
Perfect.
Folks in the crowd can chime in and tell us what you think of the mic.
Yeah, let's get some feedback from the live studio audience. Yeah.
Wally says a vacuum pump can get very close to the vacuum of space. Oh, you know what? Jaron left, but we didn't get to the thing you told me he wanted to look at, which Wally helped me with.
Oh, the ISS thing? Well, if you want, we can go over it, and I can just link on the timestamps later, because he's really wanting to, he's been asking about that for like a month now. So, yeah, we could go over that,
yeah.
That's a good question.
You want to do that one? Let's do that one real quick.
Yeah.
Let's see. All right. I'll just do a little screen share or something. Yeah, you can link it to him, or he can come back or whatever. Entire screen. Let's show that screen. Go. Am I showing? Yes, I am. Okay. So through Alan showed this to me, but I guess it comes from Jaron. Jaron was looking at Transit Finder, and I got the link there on the screen. Transit Finder for Southern Hemisphere transits. It's a website that shows when, like, the ISS or the Hubble telescope is going to go in front of the moon or in front of the sun.
I'm going to grab some water. I'll be right back.
Okay. And here I have, as an example, if you go to Cape Town, South Africa, and you punch in this is an example of something that I found. And it says that the ISS, here, I think you guys can see this, yeah. The ISS is going to pass close to the moon on this date. Now, Jaron's discovery of this is that seems backwards, because all of those satellites certainly should be going eastbound. We're told that they go eastbound, and on the northern hemisphere, these images show the satellite passing in an easterly direction, going from west to east. But in the southern hemisphere, if you're looking at the moon or the sun, Jaron reasoned that you must be facing sort of northish, and so east should be on the right side of the screen. And so this thing is appears to be headed westbound. So that's the question. Why does this thing look like it's going westbound if it's supposed to be going eastbound? And so I used mooncalc.org. This actually bounced this one off Wally, so thanks for showing up. I looked at mooncalc.org to compare whether, first of all, is this right? And then what does it look like? And let me just, I'll just show you, I'll cut right to it. Since Jared's not here, I won't take you through the whole derivation or whatever, but here it is on MoonCalc, Cape Town. Yeah, Cape Town. And at that time in that location, and we see the moon is approximately where we expect it to be, and the azimuth is approximately right. But look at the phase. The phase of the moon, and MoonCalc shows the observer's viewpoint, shows the light on the top right side, not on the left side. So that's our clue that this image is not being presented in the same way that this one is. And so I went to Stellarium after that, and that's really enlightening. So yeah, this is stellarium.org. It's an online planetarium. You can do this. Punched in the same thing, punched in Cape Town, same exact time, and then just where is the ISS? And it'll show it to you. And there's the moon. Notice the phase of the moon matches up. And if you just click, you can just click your time to advance time, and you can watch the ISS going that way, which doesn't match this direction because the orientation of this image is not the same as the viewer's orientation. So there's your answer. There's your 2-minute answer. Transit Finder shows the sky in star chart format, where north is at the top, east is on the left. They do not change the orientation based on viewing angle, and based on that, east is on the left. This is eastbound. Okay. So, Alan, are you back?
Yeah. No, I was listening. So the answer
you catch any of that?
So the answer is just how it's displayed on the website. Interesting. Well, thanks for
the website. Unfortunately, and I was disappointed by this too, it does not orient that image to match the viewer's point of view like MoonCalc does.
Gotcha, but technically it is still going in the expected directions.
Yeah. My takeaway was, or my guess is that pretty much astronomers don't care.
Right.
Once you get into fairly serious astronomy, you're going to be using a mount that is not mounted upright. You'll probably be on an equatorial mount or something, looking at everything rotated anyway. So you just really don't care anymore. So,
gotcha.
Yeah.
Makes sense.
Okay, and let's do whatever you wanted to talk about.
All right, cool. Yeah, so I wanted to do the satellite mesh network question, and then kind of ask them questions about like orbital decay and that sort of thing, and how it all calculates that, and how you guys, what do you do about orbital decay and stuff. So, and so we'll just kind of talk about that stuff. Maybe we'll get into some gravity well stuff.
Okay, you wanted to talk about, is this you describe, ask a question. We didn't do a good job with the Jaren stuff, but let's try to keep to 2-minute question. I'll give you a 2-minute answer.
Okay, yeah, give me 1 second. Let me pull up the video.
Another shout out to where's Wally there. I asked him because I know he's down there in the southern part of the world and looks up at the night sky a lot. So
yeah,
he could
thanks,
probably
Wally, for chiming in on that, dude. Appreciate it.
He could probably confirm that, like, I'm a total amateur, like, sky watcher. I have an Azel mount myself, but you guys probably don't care. I mean, that's not even like the orientation of things is probably not even in your head while you're looking at the sky.
All right. I linked the video in StreamYard real quick if you want to jump to that, and then you could just play it at 2x speed or whatever if you want, because you've already seen it, right? The mesh network thing.
Okay.
You could just kind of familiarize the audience with what's.
Is this gonna share? Let me do share screen, and I'm gonna do. one. And okay, I think I'm sharing. Let's see if we get audio.
I want to point out is what I call the 8,700 mile per hour mesh trilateration network, which is a mess. It is a problem. And the way GPS would work in space with satellites is you would have multiple satellites circling the Earth twice per day, and at a height of 20,000 kilometers, and you would use trilateration, and it uses a rate times time, basically. So it's sending pings back, and it's using trilateration between these different nodes, right? The problem is, let me put it together for you here. Our GPS satellite's geostationary. Just to kind of recap what I said, they circle the Earth at an altitude of 20,000 kilometers or 13,000 miles, and they complete 2 full orbits a day. They are not in a geostationary orbit, meaning satellites are wrapping around the Earth, right? They're not even stationary.
Yeah.
So how fast are they going? Well, there's multiple orbit calculators you can use. I checked it with several, but the one I went with was for the picture proof, so to speak, was Kaizen. And your flight velocity is 3.8, let's just round and say 3.9 kilometers per second. Okay, so what's that miles per hour? Something we should all know. That's roughly 8,700 miles per hour. That's how fast this mesh network is wrapping around the supposed sphere of the Earth. 8,700 miles an hour. And you're trying to do trilateration with that, right? So first off, for that to even work, if you talk to someone who does any type of development, right, those nodes would have to, or satellites, whatever you want to call them, would have to not move an inch in between each other. They would have to be as if they were, punched on the outside of a ball, right? Because how could, if I move my phone 6 inches, how does the mesh network not know what it was one of its nodes not moving 6 inches while it's zipping around the Earth at 8,700 miles an hour?
Okay, I think that was the question right there.
Yeah.
Right.
So basically, how do we get this this excellent accuracy, out of the whole? If the whole network itself is moving, like, shouldn't it be, to get that kind of accuracy? Wouldn't it have to be stationary? And like, what kind of things does it have to account for to get that kind of accuracy? And is it totally, like, is there an explanation for it rather? Because I've never heard that argument before, and I thought it was a really interesting one. And so
yeah, I would call that a spurious argument. Let me see if I can share this.
M-Ball, in the documents, do you see have you ever found where it shit, what was the question? What was that thing we were talking about?
M-Ball has a question?
Yeah, do you remember when we were talking about the open source stuff of GPS? What was the
I have that.
What was the thing that you hadn't found or whatever? Do you remember what we were talking about? I can't remember off the top of my head now. It was it was like how to verify what it does, because you guys always say like it's in the it's open source or whatever.
Oh yeah. I said I hadn't done it myself, but I'm about to suggest that you should.
Yeah.
Like, as a truth seeker or whatever, the truth is here. The truth shall set you free. Here it is. So there's the link to ESA, European Space Agency, just published the explanations how it all works. Let me give you the TLD, the 2-minute TLDR.
Yeah.
What do you get from a GPS signal? You get the position of the satellite and the time it sent that position. That's all. That's what you get. You say, the satellite says, hey, I am right here, and the time is this. And the satellite moves on and sends another ping. And it'll tell you, here's my position now, and here's the time now. That's what it does. Okay, and it is passive. It's not communication, like your cell phone's not communicating to the satellite. It's just listening. Your receiver only listens. Cool with all that?
Okay. Yeah.
Did you already know all that?
No. Nope.
Okay.
Haven't had time to fully look into all that. I just heard this recent, this is a recent video that just popped up, and I was like, oh, that's interesting.
Okay. So that's what you get. That's the information that you get. And so first of all, I will say, from a science perspective, the position of the satellite, boom, you're done. It's in space. It's in the position of the satellite. It says so.
Sure.
So I'm assuming you're going to come back with, yeah, but it must be lying about that.
I mean, it could be spoofed,
right?
Yeah,
it must not be giving me the correct information because it says it's orbiting the planet, right?
Yeah.
Okay.
I mean,
so here's how GPS works. Well, here's how trilateration works in the super quick. You get the position of the satellite and the distance. So you get the distance from the time. You say, oh, it said the time is this, but I got the time is this. That means it's been this long since it sent that signal, means it's this far away.
Right.
Cool. Just like we learned with seismology, like when there's an earthquake, how do we know where the earthquake is? Well, we take how long it took for the wave to get to us.
Right.
That means it's, and we do that. So then you get a second satellite and it says it's there. And a third satellite says it's there at this distance. And where those three things line up, that's where you are.
Right. Like that's not what's in contention. I just thought that the fact that they all move, separately or whatever might be
so
weird or whatever.
Let's have them move.
Yeah.
Let's have them move and see how we would react to that.
Well, it records its position as it sends the pings, like with the time you were saying, so it wouldn't really matter what it. Like that pretty much
it doesn't matter.
It. Yeah, that pretty much solves it. So yeah, I just didn't think about that. Makes sense. Like what you're saying is
all right. So I'll just go since I went through all the effort of making the slides.
Yeah, go ahead. Go ahead, send it, brother. Yeah, don't let me rain on your parade, dog. Go ahead.
Satellites move in some random direction.
Yeah.
They send a new ping. You get new pings, and they tell you where you are, just like the old pings did. And the speed of the satellites is essentially irrelevant. The relative, they do not have to stay in perfect synchronicity or anything. Any which way they move is still going to work.
Kind of a misnomer or whatever to assume that would have
that guy. Yeah, I don't know what he was talking about.
Yeah, it just slipped up on that one, because if you don't know that, it does appear to be like a weird explanation, that it's because it's assumed kind of that it's like synchronized. I don't know. So I can kind of see where he got that line of thinking,
Although if you dig in, they are moving very, very fast. So if you dig into that link that I showed earlier, and remind me, I'll throw it in the chat.
Yeah.
The ESA talks about how you have to account for Doppler shift because of the speed. The speed is so high and the accuracy is so precise that they do have to put the speed of the satellite into those calculations to refine the accuracy.
Send me that link. I'm going to send it to Dude because he seems like a genuine guy. This is just a new guy that kind of popped up that I found.
Yeah,
he seems like a nice
it's all
guy
there.
so I'm going to send that to him. And
so like Mbal said, it's all public.
Yeah,
you can get this. And what I think, so here's the deal.
Yeah,
you want to audit space. You want to audit these guys and presumably prove that they're spoofing something. You can read the raw signal and get those positions. And then what can you do with it? What you could do with it is you could do this in reverse. You could take 3 locations on the Earth, like your position, and then go like a kilometer to the east and a kilometer north and set up 3 receivers, right? So set up 3 receivers and record the raw data. And then come back and compare that raw data. What you should get, because all 3 of them, for a single satellite now, so for a single satellite, all 3 of them are receiving the same signal, right? We can't send different signals to different people. Satellite doesn't even know you're there. So the first person will calculate their distance to that satellite and say the satellite is somewhere on that sphere. The second person says, the satellite is somewhere on this sphere. And then, of course, the third person confirms that there with the satellite is somewhere on this sphere. So now you know exactly where that satellite really is, not just where it says it is. And you can compare. Is it where it says it is?
Thank you.
So yeah, if you or yours, anybody in your cohort there, really wants to know for real, where is that satellite? There's nothing they can do to hide this information.
Fair enough, man. I'm gonna, yeah.
Okay, so that was the satellite, and then you want to talk about decay, I think. Oh no, wait, let me get the link. And yeah, I do think you wanted to talk about the decay. Okay. Although maybe, you know, we'll do the decay. So there's that link in the public chat. Okay, what was it about decay?
Just how do you guys solve for that? Like, what do you do to correct for it? Like, shouldn't everything eventually end up coming back towards
it does.
Towards the Earth, right? Yeah. So, like, what?
Yeah. They have a little bit of fuel on board. You know, I think I saw somebody earlier said they have a little bit of fuel on board to keep boosting, to try to maintain.
So when they get
their orbit,
they get lower, they just when they get to where there's enough atmosphere to push back or whatever, they just kind of correct. Is that what you're saying?
Yeah, the orbit will slowly decay.
Right.
And as we say decay, I mean it gets lower and lower and lower.
Right.
And so when it gets a little too low, they'll boost back up with using the rocket fuel until the fuel runs out. And then when the fuel runs out, that's your last life. That's the end of the life of the satellite. And then as it decays, it's eventually going to burn up.
Got you. Cool.
Or crash down if it's really big.
So the orbital decay was actually in reference to the mesh network thing, but you kind of already explained that was irrelevant. So actually,
it doesn't matter.
It wouldn't even be a factor. Okay.
Yeah, cool. They update you with their position as they go.
Dude, yeah. See, I love talking to you, dude, because now you just cleared up a bunch of arguments for me that I don't have to. Okay.
Awesome.
Cool.
Awesome. In that case, there was somebody in the chat earlier. Let's do his.
Oh yeah. Do we have some questions from the chat? And then, yeah.
Well, I don't know if he's still with us. Is Philip Wright still with us? Maybe he'll watch this later. He typed in the chat before we started, and then Flat Earth Math popped on. Charles, thank you, Charles, for noticing that and tipped me off that was there, because sure enough, YouTube deleted those comments. Those comments are gone. But it was a good question that I wanted to show. Let's see if I can screen share it. And meanwhile, if there's anybody in the chat now that wants to do a question, prepare it, and I'll ask for open questions here in a bit. Okay, so this is what Philip said. Let me make it full screen so we can read it. Philip said, kind of a long explanation, but this is centrifugal force based on the Earth is spinning. So if the Earth is spinning, then you should weigh less at the equator. He calculates that. I didn't confirm his number, but it definitely looks like it's in the right scale. It seems about right. So yeah, you weigh less by this amount. Gravity is lower by this amount. And then some of that is straight up, but some of that, he says, some of that is not straight up. Some of this is going to point like in the direction of the equator. So if you're up north, this much of it is pointing to the south, not just straight up, but kind of like pulling you southbound. So he wants to know, this is how much force he calculated, and that is in centimeters per second squared. So not a big amount, but it's a non-zero amount. And the way he figures it, it should be pointing to the south. So what the heck? So Philip, I don't think you're still here, but hopefully you watch this later. Here's your answer. I do have a link to a full video I did on this, so that's there. And the 2-minute answer is, first of all, 1.46 centimeters per second squared, you said is a massive acceleration. I'm not going to call that massive. That is 0.15% of a G, right? Not 0.15 Gs, 0.15% of a G. So it's a very tiny amount, but even so, it should be measurable, right? That is a measurable amount of force. So the real answer is this pushes south, only it doesn't, because the centrifugal force that you do feel and you do measure, that centrifugal force is real. It adds together with the force of gravity. So we get the combined force is what we feel, right? That's what you're talking about. We should also feel this force, and yes, we do. It is this combination of forces that we use to level our stuff. And this is in fact why the Earth is not a perfect sphere. It bulges very slightly at the equator. The equatorial radius is larger than the polar radius. And this was originally, I think Isaac Newton himself back in the 1800s figured that out. And then after he figured it out mathematically, people went out and measured it with survey equipment and found that it was true. And then, later we go to space and take pictures and say, oh yeah, look, it is true. So I have a little from my video that I'll put the link for. I just took one slide out of it. So here we have a plumb bob. This is supposed to represent a plumb bob hanging down by the force of gravity, or you could use a spirit level, right? Spirit level, but it's the same deal. Gravity is the green arrow. It points down. That is what holds the plumb bob in place. But as you correctly point out, Philip Wright correctly points out, there is also this centrifugal force, which I'm drawing as the red arrow. I am exaggerating the red arrow here, right? This is exaggerated to show detail. In fact, it was like 0.15% of the green arrow. Okay, so they combine, and if you add those together, you get the purple arrow. The purple arrow is actually the direction that the plumb bob is going to be pulled in. So this plumb bob isn't going to hang straight down there. It's going to hang along the direction of the purple arrow like that. So if you guys are with me, I don't know, Alan, did that make sense?
Yep.
Okay, so what I'm going to do now is I'm going to take a plumb bob and I'm going to pour concrete to make a level floor under that thing. That level floor is not this. This is not the level floor. The level floor is that. That is what level is. Level includes the centrifugal force, and that's why there is no southbound component of that vector. And to sort of emphasize it a little bit, let's just straighten out the diagram so it's not cockeyed. There you go. Now we see why there is no southbound force, because the force that we use to pour our concrete level is the purple line, not the green line, because there's no way to get the green line. We don't have, right? I mean, we could maybe calculate that, but that's not what we feel. What we feel is the purple one. Okay, so that was Philip's question. And if anybody has, he's not here, but if anybody has follow-ups on that, including yourself, Alan, go for it. We did not see your other friend either.
Oh yeah, I think he's doing a stream right now about something else. So I think something popped up for him. So that's okay.
Okay. Did you remember what he wanted to ask? We could ask.
No, I don't.
Okay. Okay.
Yeah, I just told him that it was available and stuff, and to come on, and I just.
All right.
Yeah. So anyway,
did you have something else? I think maybe
um,
we covered everything that I prepped.
yeah. So do you remember when we talked about was the guy's name Ubler's paradox or whatever? How the sky should be, all basically a white light
Oh,
because of the thing, but the answer is
mhm.
basically that 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 area of space does exist. It just that light hasn't reached us yet because it's further away, right? Is that kind of what the answer was
Right,
to the paradox?
right.
Okay, so you know how
Well,
the okay,
yeah,
sorry,
and
go
it
ahead.
never will. Yeah,
Oh, really? Why
yeah.
not?
That it's
Oh, I didn't know
because
that
the
I didn't
universe
know
is
I didn't know that it was never expected to because I was going to ask you, with the so-called James Webb Telescope seeing back,
Mhm.
so much further. I was wondering if you would ever expect it to see, how the background of space is black. Would you ever start seeing just, all white? But I guess the answer is no. So why is that?
Well,
I didn't know that.
actually, yeah, sort of.
Oh yeah. Oh
You've heard of
shit.
the CMB?
Yeah, yeah. Cosmic microwave sandwich or whatever.
That's right.
Yeah.
Cosmic microwave background is everywhere. Everywhere you look in the sky, it's not white.
Right.
It's white. It was white, right, billions of years ago, but because space is expanding, it has red shifted down into the radio frequency.
Oh, I
And
misunderstood the
we
answer
see
to
it
the
as just
paradox
radio.
then. Okay.
Well,
So
both.
so
I
it's
mean,
technically still
the
there,
universe
but
is
it's just
not
not
infinitely old.
perceptible.
The answer is the universe is not infinitely old.
Right.
Um,
How do you know? You weren't
right.
there. I'm just kidding.
Yeah, I wasn't there. I'm
I don't
not.
know, man.
I'm old. I'm old, but I'm not
I'm an
that old.
infinite older universe guy, man. I don't know.
Yeah, could be, right? Well, I mean, this is the mainstream answer. The mainstream answer says that there is cosmic microwave background that we do see. We see that we are surrounded by it. So if we look far enough out, we're looking back in time. We're looking billions of years ago at a time when the entire visible universe was glowing.
Sure,
It
sure.
was white hot.
Right.
Um, and then suddenly it cooled down, and so we can't see through that.
Yeah. So I
Just a
thought
white glow.
yeah, I thought Ubler's paradox was about the light of the stars, going in all directions because it's omnidirectional. Or is that what you're talking about when you say white hot?
It's
Because
well,
that's what
I mean,
I
it's sort
thought.
of the same
That's what I thought. Okay.
nuances, right? Back when they first had the paradox, they didn't know
Uh,
about the CMB. They didn't know about Big Bang cosmology
sure,
when he
sure,
first invented this idea.
sure.
Um,
Oh, okay.
yeah, so he imagined an infinite universe
Yeah.
and infinite time. Um, so the stars should be everywhere. Every point in space should have a star there at some distance. So we should just be inundated by background light because of that.
Gotcha.
But
Well,
the
you're
truth
actually
is,
gotcha.
while space might be infinite, we have no way of knowing that. It is not infinitely old.
Hmm. Sure.
So the light, if there was a star out there, that light would not have had a chance to get to us.
Okay.
And in fact, if there is a star out there now, could be that light cannot get to us. So
Cool. That
yeah.
that actually makes sense. I guess I misunderstood what's going on there in that. So that, or I mean, it makes sense, in your guys' worldview. I thought that it was a slightly different.
Yeah,
Okay.
and well said. Right,
Yeah.
it makes sense in the mainstream science understanding. Doesn't mean you have to agree with it, but I
Yeah.
appreciate you say that it makes sense.
Yeah. Yeah. Because I heard an explanation, but it wasn't quite that. So I was like, well, that doesn't really make sense. So why do they go with that? But if what you're saying, okay. And then so there was so gravitational lensing. I wanted to ask you
Mhm.
about like lensing itself. So you know how like all lenses have a refractive index and stuff.
Right.
So
Okay.
in for gravitational lensing, right? Is there a refractive index of gravity or anything? Like, how does that work? Does there have to be one? Would you say like what's going
Um,
on there that's different from regular magnification?
it's
Because if
it's
you
similar.
because when you need because then um in like regular magnification you need some sort of actual physical lens and there's a refractive index for it.
Right.
So I was just wondering about that.
Right. A gravitational lens works without like a physical medium. It makes space become the medium.
So
the GR explanation, the GR understanding is that space is bent by space-time, I should say, and really I should say the space-time metric is distorted by the presence of mass. So if there's a mass nearby, the space-time metric is distorted there. And light follows the metric. It doesn't follow like a Euclidean straight line. It follows the space-time metric.
Which is curved, right? So
which is curved.
Which is where you get your gravity wells and such.
Right. So hopefully by saying the whole thing, space-time metric,
so
that helps to understand, no, it's not space that's bent. Space is not bent. The space-time metric is bent.
So you're saying that the path that light travels is bent.
Yes.
It's not necessarily an actual lens, like a magnification.
Well, it's not a physical. It's not. So it's not caused by refraction. It's not caused by refraction. It's caused by gravity.
So let me ask you this: are you seeing further into space than you should, or are you seeing around objects that were obscuring things? Is that what's going on?
Different stuff. Different stuff happens.
Okay.
If you have a massive object, like let's say a galaxy, we could treat a galaxy as a large ball of mass. So that will create gravity that pulls in. And so as light goes past it, the light will bend around it. Right. Light going. Yeah.
When you say you're going to like look out, you see the galaxy or whatever, how do you determine how much a galaxy weighs? Or what the expected curvature? Because wouldn't you have to isn't there some formula for the gravitational lensing or something like that? Or you just kind of, or is it like an assumption based on what you see? That's an interesting
question. That's actually pretty deep question of modern science. First off, what they do is they look at the galaxy, they look at its brightness, and they try to estimate how many stars there are in that galaxy. And based on the understanding of how much mass those stars should have, they can make an estimate of how much mass the galaxy should have. And then they look at how much the light is bent as it goes past it. Okay. And invariably, they find that those two numbers don't match, which is curious.
How do they determine the expected amount of stars? Like, what does that even mean? Because couldn't there be stars within the galaxy that are like not seen because they're being obscured by other like redder lights or something like that? Like, how could you ever really know? You know what I mean? Because it seems like in a way they could just
1, 2.
Yeah. It seems like in a way they could just kind of fill in the blank if they had a bunch of presuppositions. And I don't want to like get into that kind of discussion, where it's like, what's your presupposition or whatever. But I'm just trying to like figure this out because a lot of this stuff hinges on it. And if you're going to go as far as to say that, they're calculating the mass of the gravity or, of a galaxy at a distance, like I'm just personally curious about the process involved in that and like who determines like how many stars there should be and things like that. And I don't mean to be contrarian about it. I'm just genuinely like, what the hell's going on here?
We should ask Rob to give us a talk about that at some point.
Dude, I would love to.
I'd love to. The super 2-minute TLD is mostly based on the brightness of the overall galaxy, combined with certain benchmark events, like a type 1a supernova, for example. There's certain like standard candles, they'll call them a standard candle. There are certain things in the sky that have a known brightness. They're like, oh, that is exactly this brightness. Therefore, I can work out how far away it is. Therefore, I can work out how far the rest of it is, and then I can take, the brightness that I see of those stars based on their distance tells me how much star there is. And then they'll have to do, and it really is an estimate of how many stars would be in a galaxy in order to make it that big and that bright. And you know, when you say, yeah, but you could just make that up. Right. But if you're going to just make it up, you're not going to just invent numbers that then don't match, because then they do the gravitational lens calculation and show they don't match. And so that leaves us with a puzzle. Right. And that, I don't think if they were trying to convince everyone that they knew it all and they had all the answers, they wouldn't leave these mysteries lying on the table.
Sure.
Right.
Sure.
At least I don't think that's not consistent with the idea that they're just making it up to make it seem real, at least to me.
Right. Okay. All right. So that was what I had to ask about that. And
okay.
I think that was everything so far. So actually I was just listening to a debate, and there's still a lot of people don't think that that people are upside down on the globe or whatever relative to people in the northern, and it like it's just it's crazy because of the explanations that they go through to they don't want to believe in it either. But they still want to be on the ball.
They're just a fight. They're mostly just a fight. And so when the flat earther says, why is that guy would be upside down, and then the glober invariably refuses to admit that guy is upside down. Compared to each other, they are upside down.
Right.
Right. Compared to the Earth, nobody's upside down. That's it, right? And we should both understand that. It's not something we should be fighting about.
Right.
We should understand both points of view, that relative to us, people on the opposite side of the planet, they are upside down. But they don't feel upside down because their down is the opposite of our down. So we're all upright. Upright is a sphere. Upright is not a flat.
All right, boys. I hope that clears up the antipodal situation. Because didn't wouldn't there be like upside down planes and stuff from satellites or whatever?
Sure. I remember. I think it was you asked me to show a picture of one, and so I did.
Yeah. So
right. It wasn't upside down, but it was sideways, right?
Oh, was it? I do vaguely remember. Okay, yeah. So
it's like, and as soon as you saw it, you're like, yeah, that means nothing.
Yeah, it's like, yeah.
Of course it looks like that. That's the way it's supposed to look.
Right. Cool. So there was that.
And it does.
And so there's something going on, that people are discussing in Flat Earth right now about general relativity. And it's that if you were standing on the sun, you could say that the Earth is rotating around the sun, and vice versa. You know what I'm talking about? So what do you have? Do you have? Do you have some clarification on that?
I heard somebody talking about Mach's principle.
No, this isn't. I don't think this is a Mach's principle.
Not Mach's principle.
No, this is that would be like the translation of the motion of the sky to the Earth, creating like a centrifugal effect. I think that's what.
That's not what you mean.
No. This is related to how they say that they know that the Earth goes around the sun or whatever with the Einstein quote, but he says that no terrestrial experiment can prove it, although the Earth goes around the sun.
That's Mach's principle.
Oh, is it? Okay, sorry. I thought that was in relation to something else. Then my bad.
I think Einstein and Mach were having this argument, if I remember right. I mean, this history at this point. The bottom line, science answer is frame dragging is a thing, but it's very, very small. small enough that it's not worth discussing in this context. No, rotation is not relative. It's not.
Are you talking about I'm talking about the orbit of the Earth, not the rotation of the Earth. So
right, but it's going around in a circle, right? It's going around in a circle. So
I think we're having a miscomm here.
Okay.
I'll have to come back to it because I want to do a more extensive general relativity.
Okay, I did have a
yeah.
Well, I did have a discussion with somebody who was convinced that the Earth is stationary and the entire universe orbits around us. And I suppose you can't technically, mathematically rule it out. But it's a bit absurd.
Well, not only that, but aren't there observations that say that we're the center? Like I've read it in papers where they say that, like in your guys' like peer review stuff. So like,
well,
I know that
we're because of the speed of light and the age
right.
of the universe, we're always the center.
Sure.
Everybody is their own center of the universe. Yeah, in a certain.
Well, that's one interpretation of it.
Is that what you mean?
No.
Yeah, Eric wants to point out that it was no optical experiment, not no experiment.
There was no optical experiment.
Yeah, without
no
Einstein,
terrestrial experiment as well. There's like various quotes of it, but yeah, go on.
Without Einstein here for us to ask him and say, "Hey, Mr. Einstein, sir, what did you mean by that? Are you ruling out the Sagnac experiment? Are you ruling out?"
I would say
Michelson-Gale. Michelson-Gale. Sorry.
I would say he was,
and I don't think he was. I don't think he meant that at all.
How?
Because
he knew about.
He should have known.
Though, right? He knew about a Foucault's pendulum, right? Like how and all that kind of stuff. So why would he say that then and just like hand wave dismiss it? Because he said that there's no terrestrial experiment as well. So you're saying anything on the Earth?
I think he meant translational motion is relative. And I think he was also giving a nod to Mach, who was suggesting that if all the matter in the universe was contrived just right, the influence of the motion of the matter of the universe could work backwards. The whole thing could be worked backwards. I think.
Yeah,
but
it was like
kind of absurd to imagine that.
Is it?
but I think that maybe Einstein was saying, yeah, I mean, sort of technically you could do that. I'm not sure. Einstein's not here, unfortunately, to really clarify that.
Yeah.
What I can tell you is that no optical experiment, no experiment whatsoever can tell you absolute motion. There's no such thing. All motion is relative. There's no getting away from that. Rotational motion, however, is not. And you can make a fiber optic gyro and you can measure your own rotation, and that's. And Mach was trying to say that that's relative to the universe. So the universe could be rotating around us.
Gotcha.
And no, no mainstream scientist, I think, will accept that.
I think I've seen some quotes where they do actually. I'll get back to you on that. Like we can sidebar that and come back to it. Because I've heard some interesting arguments for and against
overgeneralizing.
Yeah,
the mainstream consensus is
right.
that no, that's not the case. But there are a few people who will take up Mach's principle for whatever.
Sure.
Yeah. So Michael Dan Olson says, yeah, but then what's the rest? Yeah. There we go.
What's that?
How does the bucket know? Yeah, it was Einstein's bucket. It goes back to, I'm sorry, not Einstein, Newton's bucket. It goes back to Newton. Newton saying rotation is not relative because of the bucket.
Does the bucket know that it is rotating if the rotation is relative?
That was Newton's point of view, right? And then Mach said that what if the universe has an influence on the water,
right,
that is causing the sides to crawl up because the universe is rotating, And to me, it just sounds like, absurd philosophy. Kind of like, what if the entire universe was created last Tuesday? And I would say, yeah, but I can see the light from Andromeda from millions of years ago. And then the answer is, well, the light from Andromeda was also created last Tuesday. And I could say, oh, yeah, but I remember 2 weeks ago. And you say, no, your memories of 2 weeks ago were created last Tuesday. It's absurd and silly, but you can't disprove it.
Yeah.
So I think it's like that.
Yeah, cool. All right, man. Well, that's pretty much all I had down. Was there anything else in the email that I sent you? I think that was pretty much it for me.
I think we covered the email. I did want to shout to anybody in the chat with us here that wants to present a question. Dr. Banner has been here this whole time and having lively chats. If there's him or anybody else who has what you would call a legitimate question that we can frame, be happy to hear that. Okay, I'll give it a minute because there is a delay on this thing. I'll close this. Anybody? I don't hear anybody. Anybody in the globe side has a question? We could do that too. Let's see. Nope, not seeing anything. Here's your chance. We'll go live, right? Why does a mechanical gyro set on the table in my house not show rotation? That's a good question. Why does a mechanical gyro not show rotation? The mainstream answer is the gyro that you're talking about doesn't have the level of precision required to show a rotation that small. There are mechanical gyros that do have enough precision to show that. So check with the manufacturer on what they state the precision of your gyro is. There's in fact a fun story from the Soviet aerospace, from Soviet space launches, where they had a satellite, a rocket on the launch pad, and they had to scrub the launch. And so they scrubbed it, but then it aborted itself and destroyed itself on the launch pad. And then when they dug back through the forensics to see why did it do this, it turned out that the gyro was still working. And while the gyro was still spinning on the launch pad, it detected that the rocket had rotated beyond mission parameters. And the reason it had rotated beyond mission parameters was because the Earth was rotating underneath the rocket and the rocket wasn't moving. And so it aborted itself. And that was a very precise mechanical gyro that was blamed for that. So, yeah. Okay, cool. Anybody else or?
So hold on, wait. So,
any other?
So you're saying if you had a mechanical gyro on like a hot air balloon, the Earth would detect the Earth rotating under the hot air balloon? Is that kind of?
You detect
is that what you
the rotation of the hot air balloon. You would detect whatever the balloon is doing.
No, okay,
yeah.
I'm sorry. Yeah, I was kind of half listening.
So yeah, I mean, if it's just like tethered, if it's just tethered to the Earth, so it's rotating at the same speed as the Earth, then yeah, that's going to be 15 degrees per hour.
No, wait. Yeah, okay. I thought you said that the rocket was like taken off or whatever, and then it detected that the Earth was rotating under it, so it aborted or something.
No, the rocket did not launch. The Russian rocket, it was aborted, so it was just sitting there. It was just sitting on the launch pad. They shut it down. They said, okay, we're not launching.
Right.
Cancel the launch.
Okay.
But the electronics are still going.
Gotcha.
The guidance system is still running. And as it was sitting on the pad, the gyro was telling the computer, hey, you're starting to lean. You're starting to lean. Hey, computer, oh, crap, we're leaning. And it said, oh, we're leaning way too much. Abort. And then it blew up. It blew itself up. And it did that as a safety measure, right? To prevent it from like flying into near town or something.
Oh, my bad. I misunderstood. I thought you said it took off and then or something, and there was
No,
some issue.
it
So it was
destroyed
just
itself on the ground.
so just detecting the
because
rotation
the
of the Earth,
gyro.
it thought that it was fucking up or messing up, and it
Yeah.
self-reported. Interesting. Okay, so that's what they say. Okay. All right.
Okay. Hey, Michael Dan
That's-
Olson says, wait, hold on. I missed. Here we go.
Dude,
You
what?
don't see satellites. You don't see satellites with the naked eye as such. Watch my recent series on what it means to be able to see details. I just wanted to point out that you can absolutely see the speck of light from a satellite with the naked eye. No problem. Lots of people see them. There's actually a recent rash of UFO reports because people are seeing Starlink satellites a lot now. They're very visible. You don't see the shape of it.
I've seen so-called Starlink
with the naked eye.
Things.
Yeah, Alan agrees. You've seen it.
I've seen it.
Yeah, and seeing them pass in front of the moon, no, you're not going to see them. I don't think you can see that with the naked eye.
Oh yeah, that was with the
many
naked eye,
many people have filmed, including Jaron himself, who was here earlier. We could have asked him about this. Jaron has filmed the ISS passing in front of the moon with his his camera. Yeah, you can absolutely see satellites. Okay, and Dr. Banner says that the most precision mechanical gyro will not show any rotation. I invite you to buy said mechanical gyro and show us that, because the manufacturers say that it does. They literally say that. Yeah, I don't have one of those, but you're welcome. Hey, Rob is here.
Yo,
Rob, we had a question
Rob?
for you, sir. We had a question for you real quick. What was it? How do you know how much mass is in a galaxy, a distant galaxy?
Well, I'm familiar with the standard candle thing. I just didn't realize that that's what they were doing with it. So he doesn't have to go into detail on that.
All right. If you want to pop on, you can pop on and answer it, or you can just type in. Yeah. Up to you, sir.
Yeah, and for any of us science contrarians out there, Professor Rob Parks, his YouTube channel, if you have questions about astrophysics and stuff like that, he's a great resource for that. He's
yeah, let me send you the link.
He'll give it to you straight and won't be.
You on Discord right now?
Be weird about it.
Copy that. Go away. Discord. Rob. Boom. There you go. You should have a link to join us. Yeah, and we're about ready to wrap up. So while we're waiting for that, so that was gyroscopes. Yeah, Alan and I actually talked about this. I don't think we were online when we were talking about it, but we went and looked it up. Just go Google it. I would invite you, Dr. Banner, just go Google it. You'll find recent articles where even a MEMS gyro now is precise enough.
Yeah,
to measure.
Which one was the MEMS? Was that the magnetic one or something like that? I forget.
MEMS, microelectronic machines, and something like that. I don't know.
Yeah, it was something I remember talking.
Tiny little microchip. It's a microchip gyro, and.
Excuse me. I don't know if you guys heard that ripped into the mic. I'm not sure if it picked up, but excuse me if you guys did. I apologize.
Oh, okay. Hopefully, Rob, you got that, and you're here. Boom. Welcome, sir.
What up, Rob?
How do I make you big?
Can you all hear me?
Yep.
Sweet.
Boom. You're big. So the question was how, because Alan was asking about, gravitational lensing.
Yep.
And I was saying that the mass of say a galaxy, as light goes past it, it bends the space-time metric and causes that light to curve, and that can act like a lens, allowing us to magnify things behind it sometimes, or just creating distortions and mirror images, fun things like that. And Alan asked the question, how do you know how much a galaxy's mass is?
So you can do this. This is a very interesting question because it actually has led to one of the prominent dilemmas within astronomy. So if you're talking about a single galaxy, you can do it either one of two ways. You can either do it dynamically or you can do it from a luminous standpoint. Now, from the dynamical point is more, or the dynamical method is much more straightforward in that the number of assumptions you need to make are smaller. So what I mean by dynamical is essentially you just use ye old Kepler's law, Newton's revision of Kepler's law. You basically just see how fast things are moving at different radii around them, from different radii from the central point. And you basically just take an integral of those various rings, add them all up, and you get the mass.
But as I recall, was it Vera Rubin discovered that that's wrong?
No, Vera Rubin discovered that. Well,
she's
what
the
she
dark
discovered
matter lady, right?
Yes.
Yeah.
And the dilemma that I was talking about is the discovery of dark matter.
Right. So when you do it with the dynamic way, you get a different answer than if you do it with the luminous way. Is that the deal?
Yes.
Okay.
So the way, though, from the luminous standpoint, the way that you want to do it, and this is the main assumption that goes into this, is you have to assume an initial mass function. And what that means is that given an initial giant molecular cloud of a given mass, how many stars of various masses is it going to produce if all of it was consumed, for example? And so if you have, from a single cloud, you would get 200 M stars or 200 stars that were about half the solar mass, and then you get one that was 40 times mass of the sun. You can get this continuum of number of stars per given mass range. And then you basically know how much each of those stars intrinsically, how bright they are intrinsically. Then you look at the galaxy in question, you find out how much light that thing is producing in total. And then you figure out, all right, if this is the initial mass function, if this is the number of stars that were produced when this galaxy was created, then I know how many stars, how many low mass stars producing a certain amount of luminosity there should be. And then I basically add all of that up. And
how do you determine when a galaxy was created?
What you can do is there are a few age metrics that you can use to determine basically roughly speaking, how old a galaxy is going to be by looking at how old the oldest stars are.
What does that mean? Because when you look at something like the James Webb Telescope images or whatever, and you see these galaxies and you zoom in on them, they're just little dots of light. So are you extrapolating from these pixels that because this pixel is this shade, it's therefore this much brightness, therefore it must be this size, this luminosity or whatever kind of thing? Is that how you're kind of working it out from the images that you're getting?
Well, so there are two ways that we can do it. And for the galaxies that are minuscule, that are basically only a few pixels across, I really don't know how much information they can reasonably get out of it, or at least I don't know how large those error bars are from the information they get.
Right. So
but you can get
how many pixels would you say? How many pixels would you say it would take to get some real good star estimations? You think?
I don't know. I don't think I can give you an answer in pixels, but what I can do is there are two ways to get data from an object.
Mhm.
There is a photometry or a photometric measurement, which is basically you look at an image like the James Webb and you plop down an aperture and you determine how much brightness there is coming off that galaxy. And you figure out not only that, but how much brightness there is across various wavelengths. Like how much of it is in the infrared, how much is it putting out in the visible, how much, they're ultraviolet, so forth and so on.
Sure.
And that'll give you some rough kind of statistics as to how bright it, what its overall luminosity is, what its overall temperature is. But really, what you want to know is, or the better way of determining things is spectroscopically. Mm-hmm. You pass that light through a prism, and you get the spectral lines of that star, or of that galaxy, and that really tells you the elemental composition of what that galaxy is.
Could you?
And based on, and so to kind of get to your pixel question, really what we want is a signal to noise of at least 10 when it comes to how significant these lines are in relation to the background that they're on, or what we call the continuum, the lines from which they stem from, in a way.
Cool. Matt, can you pull up a what's it called? Spectroscopy. I'm not gonna get the word right. You know what I'm talking about. The word he just said.
Spectroscopy of what?
Of what he just said. Could you pull up the what's it called? Like the graph for that. You know what I'm talking about, where it shows like the wavelength colors. Because I've seen what he's kind of talking about before, but I don't really have a good I don't know how to interpret what I'm looking at. So if you don't mind, could you walk me through what all that stuff means, the color shifts and all that?
Sure, let's do
and also what you're doing to get
like
that observation. Yeah, like what produces that to begin with? Like what do you look, so you're looking at the sky with a telescope and you're getting that, or like what's going on?
That particular one, so that's from the sun, and the sun, obviously, because it's so close and so bright, that is the most detailed spectra of any astronomical object you're ever going to get.
Okay.
And so
they have one at Carnegie Mellon Library that just goes down the hall and then back up the hall, and so you can just like walk right up to it. It's on paper. You walk right up to it and look at these lines. It's really cool. Anyway, go ahead.
Nice. So there are two ways. Well, let me first start by saying that this is what we call an absorption spectrum.
Yeah.
Or a dark line absorption spectrum. Yeah. And a gentleman by the name of Kirchhoff figured out what physical situation needs to happen in order for you to see this through a prism or through some spectrograph. What you need is a hot, dense, continuous source. So you have basically something that is very hot, very dense, and is putting out light at pretty much all wavelengths. Mm-hmm. And then that light is going to pass through a less dense, cooler medium. And then that light is going to continue on to the observer. And what happens is that depending on the composition of that gas the light is passing through, that gas is going to absorb certain bits of light, which correspond to certain elements, and not only just certain elements, but also certain elements at certain temperatures.
Okay.
And so those dark lines that you see running through that picture, that Matt is showing, is essentially where the atmosphere of the sun, which is primarily composed of hydrogen and helium, although as you can see, there are a lot of different metals. Thank you. In there, or heavier elements. And each of those dark lines means that there was an element, there was an atom that really was sensitive to that wavelength of light, and it absorbed that loss, absorbed that energy. Something the internal structure, as it were, of the atom changed. It then reverted back to what it was prior to that first interaction, and then the energy that it has absorbed actually gets re-emitted out of your line of sight.
So that's what
There's
the black lines are?
Those were the black lines, yeah.
Okay, so
sorry about that.
I'm sorry, the black lines are the reabsorption of what it's emitting because of its like reflecting back from its own atmosphere. Is that what you're saying? And also, what was the metals air quotes? What was that? Could you elaborate on that?
Okay,
that seemed like a really funny joke. I want to get in on that.
So
I love air
astronomers, well, it's really kind of a geek kind of joke, but so astronomers are not chemists, like in any way whatsoever. So our periodic table. So if you went to a chemist and asked them about elements, they'd be like hydrogen, helium. You got your noble gases over here. You got your rare earth elements over here. Yada yada. Astronomers, it's hydrogen, it's helium, and everything else is a metal. We don't care about differentiating them anymore.
Carbon,
and really,
oxygen, iron, yeah, that's all metals.
Oh, okay.
And really, if you want to talk about what we call metallicity, or how much of the object is made up of heavier elements, we really don't care about anything other than iron. So metallicity is typically the amount of iron in an object as a function of how much hydrogen is in an object. But that's essentially it. It's the joke is that astronomers call everything a metal. Even oxygen is a metal.
Yeah, dude, I'm breathing in some metal right now, bro.
So
heavy metal. So, I did want to show this question from Dr. David Banner, FES, who said, "What if the star was just actually blue in color?" I'm not sure if I know you've already kind of touched on it, but could you address, like, when you see the spectrum of a star and you see that it is bluer than a regular star, how do you know it's not just a blue star?
I don't know exactly what that means. Actually, can you, on this page, can you scroll down to certain other pictures?
Yeah. See if there's anything you like, or I could Google some other search image.
Yeah, kind of.
This one's kind of interesting.
That one's kind of interesting. The one above it is a little bit more interesting.
This one?
Click on that one. Click on that one. This kind of shows it. You know, I can go into stars, right? I can kind of go into black bodies and all that kind of good stuff.
Yeah, here's some stars. I definitely recognize these names on this one.
But essentially,
how's that? That's pretty good, right?
Yeah, actually, but we're go back to the previous one. So on the right, you have what we call the spectral types. There's O, B, A, F, blah 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 blah, all the way down. Now, what you can kind of see with that in that spectra is at the brightest point of the spectra, particularly for A, for example, the brightest point of that spectra looks white, bluish white, right around there. Yeah. So if you were to look at that star, an A star, through a telescope, you would see a bluish white star. If you were to look at a O star, it would look blue. Now, if you looked at, say, an M star, you can see that most of the color, most of the brightness is in the red part of the spectrum. What this corresponds to is roughly just temperature. A blue star is just simply hotter than a red star. And you can see this in everyday life if you have access to a acetylene torch and an iron bar. Once you start heating up that iron bar, it's going to turn red. And then as you continue to heat it, if it's hot enough, you continue to heat it, it's going to turn white, and then it's going to turn blue. That's just simply...
And then it's going to turn ultraviolet, and then it's going to turn X-ray.
Yeah, exactly. If you have an acetylene torch that hot, then it might be running.
Okay, no chemical burn can get an X-ray, but...
Okay. So, Rob, what about stars like that change colors? Like, have you ever looked at Arctis or whatever? It's just kind of like it's pulsing different colors. So what does that mean? Like, what's the temperature on that? Is it constantly fluctuating, or how are we seeing that over time, over like millions of years? Are we seeing like a constant temperature fluctuation in the star, rapidly going back and forth, or like what does that mean?
So so there are two ways that a star can change color.
Okay.
That I can think of off the top of my head.
Uh-huh.
There's one that's intrinsic, meaning that the star pulsates. You have pulsating variables that have periods. Depending on what type of variable we're talking about, the period of pulsation can be ranged from hours to months. As it gets smaller, it's going to get hotter and it's going to get bluer. As it gets larger, it's going to turn redder. And it can do that, like I said, from periods ranging from hours to months. But what I think you're getting to is twinkling.
Yeah. Yeah, I was just walking my dog earlier and I saw that it was twinkling and I was like, okay, so what's going on here? Are you rapidly changing temperatures or distance? Like,
no, that's the atmosphere.
So the atmosphere. So the atmosphere routinely causes that star in particular to act that way.
Well, it's causing your perception of that star to act that way. The star itself isn't changing. Why? The star itself is more than likely just boring. It's whatever color it's.
Alan, are you suggesting that particular star twinkles more than other stars?
I'm saying that, yeah, when I look up at other stars, they don't seem to be not just twinkling, like it changes colors. Like it goes from like a blue to like an orangish. Like I don't have a video camera good enough but I can see it with my eye doing it. Like it's not just like twinkling, like there's literally goes from a different.
Is it possibly just brighter than other stars or lower in the sky?
No, it's like
those would be the two major contributors. If a brighter star is going to twinkle more than its surrounding stars, and stars that are lower on the horizon are going to twinkle more than those.
Yeah, overhead. Well, I didn't have my protractor with me, but it wasn't at the horizon. It was definitely like let me see. I was looking up, so it probably would have been about, I don't know, maybe like like 60 or 70.
You can have stars over your head that twinkle. It really depends on.
Well, yeah, but Arctis does it consistently. Like this one does it like all the time. Like it just why is it that one specifically that's always affected by the atmosphere, but the other ones aren't changing colors like that?
My first guess, and it's just a guess, is that you're just paying attention to that one in particular. Kind of like when you buy a white car, all of a sudden you notice there's so many people with white cars.
Well, I noticed it because it's doing what the other stars aren't doing, and like it's doing its own thing compared to the other ones, really.
So
because you can look
tell
at
us,
the
what
other
star
ones.
is it? We're socked in with rain here for the next week, but when it clears, I'll look at the sky with you one night and we pick a star and we look and see if we see
what, dude? Yeah, that'd be awesome, man. Because I see it all the time, and I'm like, what do they eat? Like, how do they explain this? That it's doing.
Yeah, because the stars, I don't believe, Rob, I don't believe there's any stars that pulsate in any visible way that we could actually see. Is there?
Yeah, actually, there is one very famous one. Not quickly in any way whatsoever.
Oh, yeah, you mean like Tabby Star or Betelgeuse?
No. Algol or Algol. That one got its moniker. In Arabic, Algol means the demon, and the reason why I got that moniker, at least allegedly, is because if you look at that star, it has a period of pulsation or a period of. It's actually an eclipsing binary, so it changes brightness with a period of a few days. So if you are adept at determining the brightness of a star over time, you can literally distinguish it dimming and then brightening back up again, dimming.
This is happening.
So it's kind of winking at you.
Well, this is happening as like I'm seeing it right now, like not even days, bro. Like,
so you're seeing like not even seconds, or like a second it's pulsing.
I'm literally watching it change in front of me, dude. Yeah, like I just saw it's Arctis, because that's how I know what it is, because it's the only one that Arcturus or whatever. It's the only one that does it like that. Like I can go out and see. I can go out with Stellarium and see if it's doing it right now. But I saw it earlier when I took my dogs out before we did the show.
Oh, hi, kitty. We should do that. Unfortunately, Rob, I'm sorry I covered up your face with this question, but the question is, electrical charges affect the color of gases in vacuum. How are they know? Well, okay. How do we know if these gases of a star are affected by electrical charges like that? Maybe. Does that make any sense?
I think I have to admit ignorance as to how much electric charges actually change the color of a gas. I'm actually not aware that happens.
A plasma,
yeah,
with an electric charge across it will excite the atoms, and you'll get the emission lines of that atom.
Okay.
Let's talk about emission lines, I think.
Okay.
I believe who, I forgot your name again. Sorry, sir. Femi Donmez. I believe you're talking about emission lines. And yeah, when you excite atoms, they will glow in their characteristic frequencies. And emission spectra look inverted from what we're looking at. Instead of seeing a bunch of like a glow with a couple of black lines, you see black with a couple of glow lines.
Yeah.
And hopefully that's the answer. And I don't know, Rob, you want to add anything to that?
So to have we don't really deal with electric charge so much in looking at the overall characteristics of a star, because unless you're talking about the internal structure of a star creating its magnetic field, there isn't any coherent motion or coherent motion, I guess, to the plasma to really set up an electric field or electric current, or at least a coherent one in any sense.
Well, I guess let me put it this. This is the question I had when I first learned this about the stellar absorption. I'm showing some gas absorption lines here.
Mm-hmm.
When you look at a star, you see the helium absorption lines, you see the hydrogen absorption lines. Why don't you see the emission lines? Why isn't it the glowing helium lines that we see when we look at the star?
Well, so for emission lines to happen, as far as I'm aware, what you need to have happen is, so before, like I said, you have the incandescent source, the hot, dense object, and then you have this gas cloud that the light is streaming from the source through this gas cloud and then to your eye. In order to get an emission spectrum, basically you have to be kind of over here, and you're only seeing the light coming this way. So you don't really see the continuous source, but we do actually see emission spectra in certain objects, not so much stars, but mainly galaxies.
Yeah, I guess that makes sense.
So if there were emission, if you do have emission lines, so if you have this plasma that's basically within your line of sight, and you have a little bit of you have an atom over here absorbs and then redirects it, and it's still kind of within your line of sight, so it would still be an emission. What that's going to do is that's really just going to cause the overall absorption line to be less.
Right.
It's basically going to throw flux back into that line, into that absorption line.
Yeah, that makes a lot of sense. I would also stress that the emission lines are from an atom.
Yeah.
They are when an electron jumps from one state to another bound to its proton. And in a plasma, the hot core of a star, you don't have atoms, you have plasma.
Yeah.
They don't do that. They just glow with the black body spectrum that we saw. And then as that black body full rainbow makes its way out of the star, it encounters atoms in the atmosphere of the star that do the absorption and re-emission. they'll absorb and re-emit, but they're going to absorb the light coming from the center, and they're going to emit in all directions. So the emission line will get cut out a little bit. Yeah. Cool. Let's see. Here's, whoops, went into the wrong window. Hopefully we see this. Do we see that? This is what Alan.
Twinkling.
Linked.
Yes.
Yeah.
Also called scintillation.
Yeah, and right. I think this is what Rob described. This is what I would have said. It's atmosphere and it's atmospheric turbulence, disturbance, whatever. Possible explanations for why that star twinkles more than others. Maybe it's right over someone's chimney. I mean,
no. Over the next couple of days or whatever, we'll go into that further, because it's this one specifically, and it does it every night at the same. It's just so we'll see what's up.
That's
with that
interesting,
and come back to it, because if you're saying you determine it based on these colors, so I'm assuming it would be like the colors would look the same over long periods of time. But if you're seeing I'm seeing a rapid shift within seconds, it's literally pulsating like a rhythm. It has what's that word for it? Metronome or whatever. It's just it's got a beat to it. So
interesting.
Okay.
So yeah, I'm just wondering how that would work. But I guess we can.
The science answers is not supposed to.
Yeah, we can go. Yeah, we can go into it further next time. I see it, I'll send you a message on Discord, and we'll see if we can sync up and figure it out.
Yeah, my naive, my intuition is what you're witnessing is twinkling, and you may be your sky. The amount that a star twinkles is location dependent. There are certain locations that the sky is much less turbulent than it is in other locations. So it may be that your location, you just have a really horrible sky in terms of how much twinkling you get, or great sky.
Yeah, you would think though that it would affect all of them in that way, and they would all kind of go to the same rhythm of that distortion. Since they're all kind of close together in the sky, right?
Not really. Twinkling should be completely random. Like I said, it is dependent on the magnitude of the twinkling is going to be a function of brightness, of intrinsic or apparent brightness, rather. So, the fact that you're saying that if it actually oscillates from blue to red, blue to red, blue to red, continually, periodically,
that's airplane.
That's weird.
Well, that's an airplane.
No.
Yeah, exactly. That's an airplane.
Bro, I don't have the ability to. I don't have the ability to record it in any meaningful way that you would be able to see it. But when it's up, I will get you the specifics, and then you could look at it and see what's going on. And
remind me, what part of the world are you in? East Coast, West Coast?
Yeah, East Coast. I'm in Ohio.
Okay. Yeah, Rob's also East Coast.
Oh, I thought you were in California as well, Rob.
No, I'm basically 30 minutes outside of DC.
Oh, word. Yeah. Okay.
Cool. So yeah, I mean, maybe some night you guys could synchronize viewing of.
Yeah, I'm on Discord with Rob, so I'll send it. Yeah, cool.
Yeah.
And see if there's anything to this. Is it twinkling more than the other stars?
Well, after we're done here, I'm going to go out and see if it's still nice out and see if I can see it. And I'll send it to you. Because it literally does it the whole night. So
cool. Well, all right. Great show. I should be wrapping it up. Is there any last thoughts anybody wants?
Actually, I want to address something. This was a few minutes ago from Dr. David. Looking through the gases in Earth's atmosphere will change what color the star out there appears to be. Physics. Ish. Now, will the atmosphere
That's actually a really good question.
Yeah, will the constituents of the Earth's atmosphere actually change the color of a star or an astrophysical object? Not in any noticeable way. Now, this is beside twinkling, but if you were to look at something with a spectrometer, if you were to look at the spectra of a star, what you're going to have to deal with is what we call telluric lines. There are going to be absorption lines of oxygen, carbon dioxide, nitrogen, all over the spectrum. And so when you get the spectrum of a star, you have to subtract out those telluric lines. And actually, that's not a, now it's sort of trivial, but it certainly adds error. It certainly adds a certain amount of uncertainty to your measurements, which is yet again why things like JWST space telescopes are so much better than ground-based, is because they don't have to worry about that nonsense. They don't have to worry about telluric lines. And it also is another reason why, if you've ever wondered why major telescopes are on mountains, that's another reason, is to get above as much of the atmosphere as you possibly can, so you're not looking through these gases. So.
Yep. Great answer. Great question. I would do the TLDR on that is all of the stars we look at are through Earth's atmosphere. So if you compare one star to the other, if you're doing a comparison, like, oh, this one's bluer than that one, or this one's, whatever, they both have that same effect, right? So it's equal. Okay, cool. Anything else before we call it? And if there's anybody else in the chat that wants to, there's a follow-up question on that. Absorption of the gases in the atmosphere between you and the star you observe. Yeah. That's what he was just talking about, and you have to account for that. And it introduces some error, of course, not with a space telescope.
Yep.
Well, it still does actually, I guess, with a space telescope, but then you'd be looking at the space in between the hydrogen.
Well, yeah, I was going to say,
the free hydrogen
about,
that you're.
Well, that's more of interstellar reddening, which is another subject entirely.
Yeah.
And don't they say
actually there is reddening as well? That may also, I literally teach, I have lectures based on this specific thing, dealing with the Earth's atmosphere in terms of what it does to observations. So I could go on for a couple of hours as to the nitty gritty of this sort of subject. So, yeah. Yep.
And just to geek out here, I live in Los Angeles area near Pasadena. And so I'm so blessed. If you're interested in this stuff, especially if you live like near where I do, I wake up and look at Mount Wilson. Mount Wilson is like there. So, and that's where these discoveries were made, right? And you can go up there. They give tours. You can see, they won't let you touch it. You can see the telescope. Sometimes they'll let you look through them, actually.
If you've got the money.
Do they even charge?
They from what I recall, if you want to look through the 60-inch, you got to
do the overnight, I think.
You can pay, yeah.
Yeah.
And I highly recommend that, by the way.
They do school trips. Their solar telescope, they just let people look at it.
Oh, yeah.
But yeah, that's fantastic. And also Carnegie Mellon, as I was saying, is right here.
Don't they say that that the sun's magnetosphere protects or creates like a giant plasma field around us? Because I remember hearing something about Voyager having to pass through a giant plasma field or whatever.
Yeah,
right?
What we refer to that as the heliopause.
So what does that mean exactly to that we're surrounded by a plasma field? Like, so if we're looking out, should we see some sort of like wall? Like, is it illuminated? Like, what does that mean exactly when to pass through a plasma field? Is it hot?
No,
is it cold? Like, what's going on there?
It's very rarefied. So what we're talking about when we talk about the magnetosphere and calling it a plasma field or what have you, is we're talking about in that particular locality, there are a higher density of charged particles, mainly electrons, flying around at high rates of speed. And there's probably also some protons in there. What that's going to do is that's going to interfere with basically radio transmissions for primarily, and maybe some electronics, is you, like I said, you have a higher amount of moving electrons, so you're going to have a lot more electric current or electrical interference, that sort of thing.
Gotcha.
But from a visual standpoint, if you were sitting on a Voyager, I doubt you would really even notice.
Okay, yeah, because the way it's depicted from like mainstream media when this was, where the way I saw it when it was presented, it kind of looked like it was passing through like a ring of fire kind of thing. Like, and I'm like, so
Yeah,
I'm like, so are they trying to say that we're surrounded by a sphere of fire, or a sphere of plasma or something, and like, because it looks like it's illuminated in the thing that they were showing. So I was wondering about that. And then so if it's plasma, there would have to be like, that's gas, right? Like positively charged gas.
It's probably negative, but yes.
Okay, yeah.
And really,
but it's
like
some sort of
gas
some sort of gas though would have to be there for it to do that. And I was wondering, like, how do you know what gases? Like, if there's a gas that creates a plasma field, so to speak, how do you know what other gases could potentially be between you guys and the stars? Because, like you were saying, the space telescopes eliminate, the amount of gases that interfere with spectrometers. What you were, what I'm trying to say, Matt? Help me out.
Yeah,
spectroscopy.
Yes.
Spectroscopy.
But since there's a plasma field in space, that just kind of implies that there's also, gas pockets or something like that, or like remnants of gas gradients still out there. So I was wondering, does that also interfere, and do you account for that sort of thing, or?
So, for one thing, the vast amount of the universe in terms of ordinary matter is hydrogen and helium. There's roughly around 74% hydrogen, roughly 24% helium, like I said, roughly. And then everything else is in that last 1%. So finding carbon or anything like, or water out there, that's very rare if you were to look at the entirety of the night sky, for example. So if you're talking about, the heliopause, basically the transition between our solar system and extrasolar space, what you're really dealing with is basically the hydrogen atoms that have been broken apart by high energy. So really what you're talking about is just a region of space that has a higher amount of electrons passing through it because they are tied to the magnetic field lines produced by the sun. There are going to be there are going to be protons out there as well, but those are not as common as we found that those are not as common as electrons.
What does it mean when you say like we found those are not as common? Like, are you referencing like an experiment in your head or something like that?
Yeah, primarily when we've looked at cosmic rays. Cosmic rays are, which is a kind of a misnomer because it's when you think ray, you think light. Yeah, in this case, a cosmic ray is actually a particle. It's it's a piece of matter. It's not a
light. So when they say cosmic rays hit the moon, like that's an actual little baby tiny particle?
Mm-hmm. It's an electron. Most likely it's an electron.
So how does that work? How could you stand on the moon and not get fucking, shot up by little tiny electrons?
Well, that is something that is something I suppose there you do need a little bit of shielding, but again, we're talking about
how fast are they traveling? What do you mean? Like, what are they like? What could you? What?
Well, I mean, if you're talking about, I'd have to look up what the actual density is, but you're talking about like one particle within a square centimeter. And when I talk about particle, I'm talking about an electron, which is incredibly tiny.
Well, how fast is it moving? Doesn't that impact?
It's moving at relativistic speeds. It's moving at relativistic.
So speed of light. So wouldn't that like just kind of vaporize someone if it hit them, even though it's really tiny?
No.
Have you ever seen those videos where they're like, if a grain of sand is traveling at the speed of light and it hits the Earth, it would pretty much destroy it or whatever kind of thing? Is that not true? Like, what is that?
I would have to see what they were talking about with that, but no, I would not expect that to be true. I mean, it is true that, and I know Matt has to go, but if you were to look at the moon, we know that from going there, yes, we have been to the moon a few times, that there is a small layer of dust all around the moon. at least the parts that we've been to.
Mm-hmm.
And this dust, which is about on average 6 inches thick, is caused by erosion from micrometeorites and electrons smashing into it over the course of billions of years. But if you're talking about, sort of to address your concern, is that, you could get hit by a cosmic ray. Would you even notice that it was there? Probably not. Would it cause any harm? Probably not. But I can't say with absolute certainty because I really haven't looked into this. But I can tell you that this would be very, very rare events on short time scales.
Yeah, because I feel like if you were in like a pressurized suit and like an electron hit your suit, it might poke a hole in it or something. Or yeah,
no, it wouldn't poke.
Because didn't they say that the limb was actually like basically kind of like tinfoil? Like they said it was like super thin aluminum, basically.
It's very thin, yes.
So
I
like,
don't think it was tinfoil, but it might have been mylar. But I'm not.
Mylar. I think that's actually it. So yeah, so something like that, I guess, like isn't affected by it. I guess it's a non-issue then, or whatever.
It's not as big.
But you're saying it causes
not as big
erosion.
an issue.
Okay.
It's not as big an issue as it sounds like or it feels like. It's an issue. I mean, they have to, for example, they have to reboot their computers constantly on the ISS because the computers malfunction because cosmic rays at a rate that we don't have to deal with down here on Earth. So, yeah, it's a mild inconvenience. It's not like, oh my God, we're all going to die. My eyes are falling out, right? Your hair doesn't fall out the minute you leave our atmosphere.
I don't know, man. If you catch an electron to the ocular, bro, it might take your...
They do. Astronauts see them. They see them.
What?
It's been a documented phenomenon since the beginning of space exploration. Astronauts reported they close their eyes and they see occasionally a spark of light. And we think they're getting hit by optic rays. They're getting hit by cosmic rays in the optic nerve.
No shit. Dude, I've closed my eyes and seen a flash of light. Especially, like, have you ever coughed real hard and you see a flash of light?
Oh yeah.
Like I'm pretty.
Well, yeah,
like,
you're stimulating your nerves. Yeah, you're stimulating your nerves that way.
Right. So I don't know. Yeah, I don't know if that's.
But the astronauts are reporting.
I mean, we can't. Sure.
We can't like.
Right.
Show you a video of this happening.
Right.
Because it's inside someone else's eyeball.
Sure.
Right?
Sure.
But they report this, and they have ever since the very first astronauts supposedly went into orbit, right? And it wasn't expected. Yeah, so they're getting hit by cosmic rays. It's not killing them.
Okay, cool. Well, if it's not a big deal, it's not a big deal.
In fact, studies have shown that people who've spent a great deal of time in orbit have not come back with increased rates of cancer. I was just reading a study on this a couple of months ago, I think. Rob, did you happen to see that one?
No, but this may be
bone loss and muscle loss and various other ailments that they come back with. But you'd kind of expect astronauts to have cancer from it.
Yeah.
And they just don't. So
I remember reading that the cosmonauts did at a high rate of cancer, but I think that was mainly because the Soviets really didn't care about radiation shielding. That was one of the things they were like, weight. Obviously there's the weight problem. They're like, we don't need to add radiation shielding because that's just going to add more mass. So they just, but I read that a long time ago. So,
I'd be surprised if they'd even admit that the cosmonauts had cancer. I don't know. Maybe, I don't know. They were certainly famous people that were trotted out in front of the cameras. So if, they would report the death of a famous cosmonaut, I suppose. Yep. That's cool.
I guess my last thing. Thank you for having me on. I really
thanks for coming on at zero announcements.
Yeah, no problem. I was just checking my phone and saw that you were on there.
Thanks for coming on, man. I was hoping that we could get a chance to talk, because it's always nice to. I've always had good interactions with you, and it's always fun to get answers to questions that are just, you know.
I have not been overly well the last month or so, but I'm seeming to get out of it. But the last thing I want to really say is somebody mentioned Universe Sandbox. I like that program, and I like it for its visualizations. But I think, as was mentioned it's more of a game than a science tool. That's true. There are problems with Universe Sandbox, and mainly because of just the processing of your computer. Because what you can do is one of the main problems that I have with it is how much gravity it considers. You can actually adjust sort of the n-body problem. All right, it only considers, if you have a cluster of 1,000 stars and you want to see how this thing evolves over time, you can set it so that only the gravity between like 10 of those stars actually causes any difference, or 150, or I don't know what the upper limit is, but it really depends on the processing speed of your machine. So it's not, so for large scale simulations like that, like galactic simulations, it's really more of just a kind of a nifty tool, but I wouldn't put in a lot of stock into it.
Okay. Yeah, there's a follow-up question on the radiation thing. I wonder if anybody knows the answer to this. Dr. David Banner again asks, how did those radiation shields work out for the Artemis Orion ship? And I would start us off with, let me back up just a second and start off with what I know of Dr. David Banner's comments so far. I think that this is supposed to be snide, but it's not snide. This is serious science. This is a serious science question. They sent up Orion unmanned with nobody on it, but they did have a dummy in the cockpit wearing a mock-up of the suit with sensors all over it, so they could record a tremendous amount of data on that very topic, because they're a little bit concerned. They're interested in that. Now,
why are they concerned about it?
Well, the radiation is definitely going to be increased. Like, they're going through the Van Allen belts, they're going out of our protected magnetosphere. So,
but haven't they already?
They're going to have increased radiation.
What's the new difficulty though?
It's nothing new. Nothing new. It's always been there. So what's new is they have better sensors for it.
I've asked you about the radiation with the Van Allen thing before, and you said that it's a non-issue. It's not lethal. It's not a big deal. How much radiation is too much radiation? But they're obviously concerned about it, and it would be lethal. So
no. Okay, just because they want to measure it, we should not answer, oh, it must be lethal.
Okay, fair enough.
We can't make that connection.
Fair enough. Okay, absolutely.
But they know that it is up there, and the understanding is that that's not a healthy thing.
Sure.
For human bodies, and so, you know what? The first run is unmanned, but they did put a dummy up there with sensors. Now, I wondered if anybody has seen yet, have they released any of the findings on it yet? I haven't looked, but I do think it's probably a little soon to be seeing that data back.
Well, there is, what is this? No, that's 2017. So no, that wouldn't work. Yeah, I haven't looked. I would think that by now they would have put out maybe some kind of, press release, but some small paper that basically just said, "Hey."
Yeah, there might have been, but I have a strong feeling it was a nothing burger of a paper that nobody cared about, because it said, yeah, they received the exact amount that we predicted, and it's well below anything dangerous. we're good. And
probably in an engineering journal somewhere.
And nobody cares about that.
Totally.
Right? If it's not, oh, we have to scrub the mission, or we got new pictures back from something, right? The press doesn't care about that. And also, yeah, Howie Howens, oops, I missed. Howie Howens does point out it could be lethal to electronics. And it is, yeah. And I talked to Alan about this at some length. The way we approach this is, first of all, we do try to shield the electronics. But ultimately, the ultimate solution is you have redundant electronic systems. So if you have a flight computer, you do not have one flight computer. You have 3 flight computers, probably 4. And the reason you have 3 is they vote, right? You run the program on all 3, and if a cosmic ray comes in and causes an error, it would not cause the same error on all 3. It would cause one of them to malfunction, and that would then be detected because it doesn't match the other 2. That one needs to be rebooted. And that's how we protect ourselves. And yeah, even aircraft do this. So, okay. Okay, Michael Dan Olson says...
This is from the ESA on the Artemis mission.
Yeah.
I think he's talking about the Van Allen belts. Yeah,
it was. Okay. Yeah, from ESA on the Artemis mission, he got cut off before the interesting part, I'm afraid. But yeah, we're good. Was the short answer, I think.
Yeah.
Yeah, Tyson. I read that the Apollo astronauts received as much radiation in a month as someone on Earth would experience in a year. Is that accurate? I don't remember the exact number, but it was something along those lines. They got the equivalent of a series of X-rays, I think. Something that you wouldn't like deliberately do to yourself just for giggles, but not something that's considered anywhere near a lethal dose.
You guys don't X-ray yourselves every morning before you start your day?
I try not to. I've been trying to kick that habit.
Oh, just my head. Just my head, right?
Yeah.
Yeah. Okay. Yeah, and as far as me turning into a pumpkin, it is midnight. I should wrap this up, mostly just because of the criticism from viewers of these long streams.
How long have you been going at this?
We're about to hit hour 3. So,
okay.
So yeah, probably good to wrap it up. It's great talking to you guys, as always, and the folks in the chat. And there's been some really good topics that have come in here. I think I see Flat Earth Math lurking, so I'll give you a shout too. It's good to see you back online once in a while. Loved your puzzle that you posted earlier today. The whole family, we all did it. I was late picking my daughter up from swim practice because I was working on that problem. Did you do that one, Rob? Did you see it?
No, I haven't seen it. I'll look at it.
Go check it out. It's a fun little geometry problem. So, yep. And yeah. And Dr. Banner FES says, thanks for answering my questions. Thanks for being here and having good questions. Some of those were really good questions.
Yeah.
That spark a really good conversation. And that's what this is about. All right. Awesome. Well, I will wrap it up. Thank you guys. And I'll see you on the next one. Hopefully it won't be a whole nother semester before we do it, but we'll have to see. Sure. All right. Good night, folks.
All right. Thanks, guys. Appreciate your time. And guys have a good night.
Oh, where's Wally? Hi, Wally.
Bye, Wally.